Close your eyes for a moment and imagine standing in a dimly lit room in ancient Alexandria around 300 BCE. The air carries the scent of oils and preservation herbs, mixed with something harder to name. Anticipation, perhaps, or the weight of transgression. You're about to witness something that has never happened before in recorded human history. The deliberate, systematic opening of a human body to understand what lies beneath the skin. This is not an act of violence or desecration, but something revolutionary. The birth of anatomical science. Tonight, we'll walk together through that threshold, exploring not just the physical act of that first dissection, but the courage, controversy, and profound transformation it sparked in how humanity understands itself. For thousands of years before this moment, the human body remained a mystery wrapped in taboo. Ancient civilizations had theories, of course. The Egyptians, masters of mummification, removed organs with ritualistic precision, yet they never truly studied what they extracted. Their concern was the afterlife, not understanding. The heart stayed in place because they believed it held intelligence and memory. The brain, scooped out through the nose and discarded, was considered mere stuffing with no particular purpose. Ironic, isn't it? They preserved bodies with extraordinary skill while fundamentally misunderstanding their function. The canopic jars that held the lungs, liver, stomach, and intestines were labelled and protected, but the organs within them were treated as sacred objects rather than biological structures worthy of investigation. Think about what that means for a moment. These ancient embalmers handled human organs daily. They felt the texture of a liver, the weight of lungs, and the slipperiness of intestines. They knew that hearts were muscular and that brains had a consistency somewhat like custard, yet the leap from handling to understanding never occurred. The cultural and religious framework within which they operated made such investigation literally unthinkable. The boundary between the sacred and the scientific was absolute. The Greeks before Alexandria relied heavily on animal dissection. Aristotle, that titan of philosophy, dissected creatures great and small, chickens, fish, and even elephants when he could manage it. From these observations, he extrapolated to human anatomy, sometimes brilliantly, sometimes disastrously. He believed the heart was the seat of intelligence and that the brain existed primarily to cool the blood like a radiator cooling an engine. It's easy to smile at this now, but consider his position. Without the ability to look inside a human being, he was piecing together a puzzle with half the pieces missing and several from entirely different puzzles mixed in. His logic was sound. His data was incomplete. Aristotle did make genuine contributions to biology. He classified animals with remarkable insight, identified homologous structures across different species, and understood that nature followed patterns that could be discovered through careful observation. He recognized that the heart was central to life, noting that it was the first organ to develop in embryos and the last to stop at death. He just placed the wrong function in the right structure. The heart pumps blood, yes, but it doesn't think, feel, or reason, though our language, even now, suggests otherwise when we speak of knowing in our hearts or following our hearts. The prohibition against human dissection wasn't arbitrary cruelty or ignorance. It emerged from deep-seated beliefs about the sanctity of the body, the nature of the soul, and the proper treatment of the dead. Most ancient cultures believed that the body needed to remain intact for the afterlife, or that disturbing the dead would anger the gods, or that the soul might somehow still be present and suffering. These weren't superstitions to be dismissed lightly. They were sincere attempts to honor the dead and maintain cosmic order as people understood it. The dead were still, in a sense, people. They might have journeys to complete, judgments to face, and reunions to experience in whatever realm came next. Greek culture had particularly strong taboos about touching corpses. A person who handled the dead became ritually polluted and required purification before rejoining normal society. Graves were sacred spaces, protected by law and custom. Disturbing them was a serious crime, both legally and morally. The dead could send dreams, influence the living, and demand proper respect. In Homer's Iliad, the ghost of Patroclus appears to Achilles, begging for burial so his spirit can rest. The proper treatment of the dead wasn't just about hygiene or sentiment. It was about maintaining the cosmic order and respecting the continued existence of the deceased in some form. But Alexandria was different. Founded by Alexander the Great in 331 BCE and developed under the Ptolemaic dynasty, this Egyptian city became a crucible of learning unlike anywhere else in the ancient world. The Great Library of Alexandria drew scholars from across the known world. The museum, literally a temple to the Muses, but functioning as a research institute, housed mathematicians, astronomers, poets, and physicians. The Ptolemies, Greek rulers of Egypt, were surprisingly progressive in their support of scientific inquiry. They wanted their city to be synonymous with knowledge, and they were willing to break with tradition to achieve it. They understood that patronage of learning enhanced their prestige and legitimacy. Alexandria's unique position helped make the impossible possible. As Greek rulers of Egypt, the Ptolemies were somewhat outside the strictest Greek cultural constraints. Egypt had its own traditions of dealing with the dead, quite different from Greek customs. The city was cosmopolitan, a meeting place of cultures where ideas could cross-pollinate and traditional boundaries could be questioned. The Ptolemies also had access to a steady supply of executed criminals, people whose bodies, in that society's view, were already forfeit. If a person had been condemned to death for crimes, the reasoning went, what further claim did they have to bodily integrity after execution? This reasoning troubles us now, and it troubled people then too. Using the bodies of criminals created a class distinction in death. The honoured dead kept their integrity, while the dishonoured became objects of study. It established a precedent that would haunt anatomical science for centuries. The bodies dissected were almost always those of the poor, the criminal, the marginalised, and those without family to protect their remains or voice, to object to their treatment. The knowledge gained benefited everyone, but the burden of providing that knowledge fell on those least able to refuse. Enter Herophilus of Chalcedon. Born around 335 BCE, he arrived in Alexandria as a young physician, trained in the Greek medical tradition, but burning with questions that couldn't be answered by philosophy alone. We don't know much about his early life. Ancient sources are fragmentary, and many details are lost to time. But we know he studied under Praxagoras of Kos, a physician known for distinguishing between arteries and veins, and for believing that arteries carried pneuma, a vital spirit or air, while veins carried blood. Herophilus would build on this foundation and correct its errors. History remembers Herophilus as the first person to systematically dissect human cadavers for scientific purposes. The ancient sources also suggest, disturbingly, that he may have performed vivisection on condemned criminals, examining living bodies. The Roman encyclopedist Celsus, writing 3 centuries later, claimed that Herophilus and Erasistratus vivisected as many as 600 people. This number seems impossibly high and likely reflects exaggeration or misunderstanding. Other ancient sources dispute whether vivisection occurred at all, suggesting that critics of dissection spread such rumours to discredit the practice. Let's focus on what we know with more certainty. His work with the dead. Imagine Herophilus's preparation for that first cut. He would have obtained permission from the Ptolemaic authorities, who saw value in advancing medical knowledge. The body before him might have been an executed criminal, or perhaps someone whose family had donated their remains to science. A concept so novel it barely had words to describe it yet. The room would have been prepared carefully, with tables, instruments, assistants, and perhaps observers from the medical school. Light would have been crucial, probably oil lamps and daylight through windows, as much illumination as could be arranged. His tools were simpler than you might think. Sharp knives of bronze or iron, some curved, some straight. Probes and hooks for lifting and separating tissues. Perhaps some early forceps. No anesthesia for living subjects, of course. That wouldn't be invented for 2,000 more years. No real understanding of infection or sterilization. Just keen eyes, steady hands, and questions that had burned in human minds since we first became aware of our own mortality. The instruments would need frequent sharpening. Tissue dulls blades quickly, and precise cuts require sharp edges. That first incision, can you picture it? The blade meeting skin, that initial resistance, then the parting of tissue. Human skin is tougher than you might expect, especially once the body has cooled. It has a texture, a thickness, and layers that separate under the knife. Below the skin lies fat, its amount varying from person to person and from location to location on the body. Then fascia, that tough connective tissue that wraps muscles like plastic wrap. Then muscle itself, striped or striated when you look closely. Fibrous, tougher than skin, but yielding to a sharp blade. Herophilus would have proceeded methodically, documenting what he saw, comparing it to animal anatomy he'd studied, and noting similarities and differences. The chest cavity opening to reveal the lungs, those spongy organs so different from the solid liver. Touch a lung and it compresses, springs back, and feels almost like foam. The heart, that muscular pump, finely seen in its proper context rather than imagined as the seat of thought and emotion. It's larger than you might expect, about the size of your closed fist, nestled between the lungs, and enclosed in a slippery sac called the pericardium. Even still, it's recognizably a pump. The chambers visible when opened, the valves discernible, and the thick muscular walls obvious. What Herophilus discovered revolutionized medicine. He identified and named the duodenum, that first section of the small intestine just past the stomach. The name comes from the Latin word for 12, because it's roughly 12 finger widths long, a wonderfully pragmatic way of measuring before standardized units existed. He recognized that this section had a different structure and function from the rest of the intestine. It was thicker walled and more vascular, and it was where the most intensive digestion occurred. He traced the intricate pathways of nerves, distinguishing them from tendons and blood vessels, a confusion that had plagued earlier anatomists working only with animals. Nerves are whitish, cord-like structures, tougher than blood vessels, but more delicate than tendons. In a fresh body, they're slightly translucent. They branch repeatedly, forming networks of astounding complexity. Herophilus discovered that nerves connected to the brain and spinal cord, not the heart, beginning the long process of relocating intelligence from the chest to the skull, where it actually resides. This was genuinely revolutionary. For millennia, humans had believed that thinking happened in the heart. The language of ancient texts reflects this. The heart was where decisions were made, where personality resided, and where wisdom or foolishness originated. Finding that nerves traced back to the brain suggested that this gelatinous organ in the skull, not the powerful muscle in the chest, was the true seat of sensation and control. It must have been a moment of profound cognitive dissonance for those who first understood it. Everything you are, everything you think and feel, originates in this structure that the Egyptians considered worthless enough to discard. His work on the brain itself was groundbreaking. He identified the cerebrum and cerebellum, noting their different textures and positions. The cerebrum, the large convoluted structure that fills most of the skull, has a folded surface that increases its area, like crumpling paper to fit more of it into a limited space. The cerebellum, positioned below and behind the cerebrum, has a different, tighter folding pattern and a somewhat firmer texture. Herophilus couldn't have known their specific functions, but he documented their existence and basic structure. He traced the ventricles, those fluid-filled spaces inside the brain, and developed theories about their function. The ventricles are strange to encounter in dissection. You cut into what appears to be solid tissue, and suddenly find a cavity containing clear fluid. Ancient anatomists often believed these spaces were where thought actually occurred, perhaps because they contained this mysterious cerebrospinal fluid. The idea of ventricular function persisted for centuries, with elaborate theories about how sensory information was processed in one ventricle, rational thought in another, and memory stored in a third. He even described the confluence of venous sinuses at the back of the skull, which would later be named the torcular hierophyllae in his honor, a naming that persists in medical textbooks today, over 2,000 years later. This is the point where several of the major venous channels draining blood from the brain meet, forming a kind of crossroads. It's not visible from the outside, of course. You have to remove the top of the skull and carefully lift away the brain to see the dura mater, the tough membrane beneath, and observe how the venous sinuses are embedded in it. Working alongside Herophilus was Erasistratus of Ceos, slightly younger and equally brilliant. Together, they transformed Alexandria into the world's first true centre of anatomical research. Where Herophilus focused broadly across many systems, Erasistratus developed particular expertise in certain areas. They would have discussed their findings, compared observations, and challenged each other's interpretations. This collaborative aspect of their work established another important precedent. Anatomical knowledge advances through shared investigation, not individual revelation. Erasistratus focused particularly on the vascular system, distinguishing between arteries and veins, something that seems obvious now but was revolutionary then. He noticed that arteries had thicker walls than veins and proposed that they carried pneuma, a vital air or spirit, while veins carried blood. He was wrong about the pneuma, but the observation about structural differences was spot on. If you cut an artery and a vein of similar size, the difference is immediately apparent. The artery's wall is thick, tough, and elastic. The vein's wall is thinner, more delicate, and less springy. Why did he think arteries carried air? Because when you dissect a dead body, the arteries are often empty or contain very little blood. After death, the heart's final contractions tend to push blood out of the arteries into the veins, which have more capacity. The arteries then collapse somewhat, looking almost hollow. Touch them, and they feel different from veins full of clotted blood. In living animals that Erasistratus dissected, cutting an artery caused blood to spurt, but he interpreted this as blood rushing from nearby veins to fill the vacuum created in the artery, rather than understanding that arteries normally carry blood under pressure. Erasistratus also made detailed studies of the heart's valves, those remarkable one-way gates that keep blood flowing in the correct direction. He described them with such precision that later anatomists could follow his descriptions to find them. The heart has 4 valves, 2 between the atria and ventricles, and 2 where the great vessels leave the ventricles. They're thin, flexible flaps of tissue reinforced with fibrous cords. Open a heart and you can see them, delicate and precise, engineered by evolution to handle billions of open-close cycles over a lifetime. He traced the branching patterns of blood vessels, noting how they divided into smaller and smaller channels, though he couldn't see the microscopic capillaries that actually connect arteries to veins. Those would remain invisible for another 2,000 years, waiting for the invention of the microscope. But his observations were correct as far as they went. Vessels do branch repeatedly, each division creating smaller channels, like a river dividing into streams and then rivulets, until they become too small for the naked eye to follow. Erasistratus proposed something close to a theory of circulation, suggesting that vessels formed a connected system, but he couldn't quite make the conceptual leap to understanding that blood flows in a continuous circuit. The evidence was there. Vessels connecting, blood moving, but the theoretical framework to interpret it correctly wouldn't emerge for another 18 centuries. Science often works this way. Observations accumulate, pieces of the puzzle appear, But the final insight that makes everything make sense can elude even brilliant minds for generations. The impact of their work rippled outward immediately. Medical students came to Alexandria from across the Mediterranean world to study with these pioneers. The city's reputation as a center of learning grew. Surgical techniques improved dramatically when physicians actually understood what lay beneath the skin. The treatment of wounds became more sophisticated. If you know where the major blood vessels run, you can avoid cutting them accidentally. If you understand which organs are vulnerable to particular injuries, you can assess damage more accurately and predict outcomes better. The understanding of disease shifted from pure theory to something more grounded in observable reality. Earlier medical systems, like the Hippocratic theory of 4 humours, blood, phlegm, yellow bile, and black bile, were elegant but abstract. They explained illness as imbalances without reference to actual physical structures. Anatomical knowledge didn't immediately overturn these theories, but it began the process. When you can see diseased organs, observe tumours, and identify structural abnormalities, it becomes harder to explain everything through abstract humoral imbalances. But the backlash was inevitable. Conservative voices in Alexandria and beyond were horrified. Cutting open the dead violated deeply held beliefs. The rumoured vivisections, if they truly happened, provoked even stronger outrage. Imagine performing surgery on a living person who was conscious, able to feel everything, and screaming. Even if the subjects were condemned criminals, which was the justification offered, the ethics were and remain deeply troubling. The knowledge of where nerves ran and how muscles attached might be gained, but at what cost? Critics argued that the moment of death changed the body fundamentally, so observing corpses couldn't reveal truths about living physiology. They had a point, actually. Death does change tissue. It cools, stiffens, and loses its responsive quality. Blood clots and settles. Muscles relax or contract into rigor mortis. The colours fade. Some anatomical truths are clearer in death, but some are obscured. The response to stimulus, the warmth of active metabolism, and the flow of fluids, these require living tissue to observe properly. Religious authorities raised concerns about the soul and the afterlife. Philosophers debated whether the knowledge gained justified the means. The general public, always somewhat squeamish about medical matters, recoiled from the imagery. There were limits to Alexandria's progressiveness, and Herophilus and Erasistratus had found them. The practice of human dissection, so briefly permitted, began to face increasing restrictions. It's not entirely clear when the practice stopped, but by the end of the 3rd century BCE, human dissection in Alexandria had ceased. After these pioneers died, the golden age of Alexandrian anatomy faded quickly. Subsequent generations of physicians were prohibited from dissecting human bodies. The work of Herophilus and Erasistratus was preserved in manuscripts and memories, but it couldn't be replicated or expanded. Medical education returned to animal dissection and philosophical speculation. The door that had opened so promisingly was closing again, and it would remain mostly shut for centuries. The knowledge gained wasn't lost exactly, but it couldn't grow. Anatomy became a matter of reading texts rather than making observations. This pattern would repeat throughout history. Brief windows of opportunity when dissection was tolerated or encouraged, followed by longer periods of prohibition. Each interruption delayed medical progress, though the knowledge from earlier periods was usually preserved, copied and transmitted, waiting for the next generation brave or fortunate enough to verify and extend it. Galen of Pergamon, working in the Aoud, 2nd century CE, became the most influential physician of antiquity and the medieval period. He was brilliant, prolific, and supremely confident, perhaps overconfident. Born in 129 CE in what is now Turkey, he received an excellent education and travelled widely. studying at the great medical centres of his time, including Alexandria. He served as a physician to gladiators in Pergamon, which gave him extensive experience with traumatic injuries and a practical knowledge of anatomy glimpsed through wounds. Because he couldn't dissect humans, he worked primarily with Barbary, macaques, pigs, and other animals, extrapolating to human anatomy. This worked better than you might expect, since mammals share many structural similarities. We're all variations on a common theme: hearts with 4 chambers, lungs divided into lobes, digestive systems running from mouth to anus, and skeletal structures built from similar bones arranged in similar patterns. But the devil is in the details, and Galen's extrapolations introduced numerous errors that would persist for over 1,000 years. Galen's mistake about the liver having 5 lobes, true in dogs but not humans, was taught as fact until the Renaissance. The human liver has only 2 major lobes, though the right lobe can be subdivided further. This seems like a minor error, but imagine a surgeon operating based on Galen's description, expecting to find 5 lobes and finding 2. It would create confusion, doubt, and possibly dangerous mistakes. His description of the rete mirabile, a network of blood vessels found in hoofed animals but not in humans, was assumed to exist in us as well. This structure does exist in cattle, sheep, and some other animals, at the base of the brain, but humans simply don't have it. Yet generations of anatomists read Galen's descriptions and either convinced themselves they saw it or assumed their particular specimen was abnormal. His theory that blood vessels originated in the liver rather than the heart, and that blood was consumed by the body rather than circulating, seemed logical given his observations, but was fundamentally wrong. The liver is large, vascular, and obviously important. Blood enters it from the intestines, carrying nutrients absorbed from food. Galen could see these vessels and reasoned that the liver must be manufacturing blood from the nutrients, then distributing it throughout the body where it was consumed as fuel. The heart, he thought, was secondary, important for spreading pneuma from the lungs, but not the source or primary pump for blood. Yet Galen's authority became so absolute that questioning him was almost like questioning scripture. His writings were comprehensive, detailed, and written with rhetorical skill that made them convincing. He claimed to have performed countless dissections, which was true even if they were on animals rather than humans. He wrote with confidence and addressed objections to his theories systematically. He dominated medical education so completely that for more than 1,000 years, learning medicine meant learning Galen. This created a paradox. Galen himself was an observational scientist, carefully dissecting and documenting what he saw. But his later admirers treated his conclusions as unchallengeable truth, abandoning the observational method he had championed. They memorized his texts rather than replicating his investigations. Medical education became scholastic rather than empirical, focused on interpreting authoritative texts rather than examining bodies. Christianity's rise complicated matters further. Early Christianity inherited Jewish prohibitions against desecrating corpses and added its own concerns. The belief in bodily resurrection made the idea of cutting up the dead even more problematic. If bodies were to rise again at the end of days, shouldn't they remain intact? The Church didn't explicitly forbid anatomical study in most periods, but the overall cultural atmosphere made it unthinkable. There was no direct prohibition in Scripture against dissection, but the general reverence for the body as the temple of the soul, combined with natural squeamishness and respect for the dead, created powerful barriers. Europe entered the medieval period with advanced medical texts from Greece and Rome, but no practical means of advancing beyond them. Universities emerged and medical schools were established, but they taught from books. A physician's education consisted of reading Galen and other authorities, learning therapeutic techniques, and studying herbal remedies and dietary regimens. Surgery was considered a lower-class occupation, practiced by barbers and craftsmen, rather than university-educated physicians. The idea that cutting open bodies might advance medical knowledge was barely considered. The Islamic world preserved and expanded upon ancient medical knowledge during Europe's early medieval period. Physicians like Ibn Sina, known in the West as Avicenna, wrote comprehensive medical encyclopedias that synthesized Greek, Indian, and Islamic knowledge. His Canon of Medicine, completed around 1025 CE, became the most influential medical text in both Islamic and European medicine for centuries. But they too worked within cultural and religious constraints that generally prohibited human dissection. Islamic law, like Jewish and Christian tradition, emphasized respect for the dead and the importance of burial. The body was to be washed, shrouded, and buried promptly. Dissection was generally not permitted, though Islamic scholars debated the issue. Some argued that necessity could override prohibitions. If dissection could save lives by advancing medical knowledge, perhaps it became permissible or even obligatory. But this remained a minority view, and practical dissection remained rare in Islamic regions. They refined surgical techniques, developed sophisticated pharmacology, and made remarkable clinical observations. But the interior of the human body remained largely theoretical territory. Islamic physicians made significant advances in ophthalmology, developing innovative surgical treatments for cataracts. They studied and treated kidney stones, compound fractures, and various diseases. But their knowledge of internal anatomy came primarily from Galen and animal dissection, with all the limitations that entailed. The reawakening came gradually, beginning in the medieval universities of Europe. The first sanctioned human dissections for educational purposes occurred in Bologna, Italy, around 1315. These were carefully controlled, almost ritualistic events. A body, usually of an executed criminal, would be dissected by a surgeon following instructions from a professor reading from Galen's texts. The point wasn't to discover new information, but to illustrate what was supposedly already known. If the body didn't match Galen's description, the assumption was that this particular body was abnormal, not that Galen might be wrong. Picture these early anatomical theatres. Bodies dissected in winter when decomposition was slowest. Since preservation techniques were still primitive, the procedure had to be completed quickly, often in just 3 or 4 days, before decay made further examination impossible or unbearable. The smell must have been extraordinary, even in cold weather. Fresh human tissue has its own distinctive odour, not yet the overwhelming stench of advanced decay, but certainly noticeable, organic, and slightly metallic from the blood. Observers, medical students, curious nobles, and sometimes the general public would crowd around, straining to see, probably grateful to be at some distance from the table. The Anatomical Theatre in Padua, built in 1595 and still standing today, gives a sense of these spaces. It's steeply raked, with concentric rings of standing room rising up from the central dissection table. Candles would have provided light, their flickering flames casting dramatic shadows. The atmosphere would have been part lecture, part spectacle, and part sacred ritual. The hierarchy was rigid. The professor, representing theoretical knowledge and university education, stood at a high lectern, reading from authoritative texts. The surgeon, a practical craftsman of lower social status, performed the actual dissection, following the professor's instructions. An assistant pointed to structures with a long rod as they were mentioned in the text. This division reflected medieval society's distinction between intellectual and manual labour, between theory and practice. It also made advancement of knowledge difficult. The person with anatomical training and understanding wasn't the one with their hands in the body. These dissections were annual or semi-annual events, not regular occurrences. A medical student might see only 2 or 3 human dissections during their entire education. The rest of their anatomical training came from books, lectures, and animal dissection. It's remarkable that medicine advanced at all under these constraints, but the human body is resilient enough that treatments based on imperfect understanding could still sometimes work, at least well enough to keep patients alive. And physicians did accumulate practical knowledge from experience. Even if their theoretical understanding was flawed, they could observe which treatments seemed to help and which made things worse. The true renaissance of human anatomy came with Andreas Vesalius in the 16th century. Born in Brussels in 1514 into a family of physicians and apothecaries, Vesalius showed early interest in anatomy. As a student, he reportedly stole a corpse from the gallows outside Leuven to study its anatomy, an act that was both illegal and dangerous, but reveals his passionate commitment to observation over received wisdom. He arrived in Padua, Italy, as a young medical student and immediately began to question everything he was taught. Where his professors saw Galen's descriptions confirmed in each dissection, Vesalius saw discrepancies. He started performing dissections himself rather than leaving them to surgical assistants, examining each structure carefully, comparing what he saw with what the ancient texts claimed. This was revolutionary in itself. A university professor performing manual work, getting his hands bloody, and insisting that direct observation trumped textual authority. He essentially merged the roles of professor and surgeon, embodying in one person the theoretical and practical knowledge that medieval tradition had kept separate. His students responded enthusiastically. They found his lectures engaging precisely because he was showing them real anatomy rather than just reading descriptions. He encouraged them to look, to verify, and to think critically. He performed dissections that lasted weeks rather than days, taking time to reveal structures systematically. He developed new dissection techniques, better ways to expose organs without damaging them, and methods for preserving specimens so they could be studied for longer periods. In 1543, at just 28 years old, Vesalius published De Humani Corporis Fabrica, on the fabric of the human body. This monumental work contained detailed descriptions and, crucially, beautiful illustrations of human anatomy based on direct observation rather than ancient authority. The illustrations created by artists in Titian's workshop were unprecedented in their accuracy and detail. They showed bodies in lifelike poses, muscles arranged in layers that could be mentally peeled back, and bones displayed from multiple angles. The quality of these images meant that even people who never saw a dissection could gain a real understanding of human structure. He corrected hundreds of Galen's errors. He showed that the human liver had fewer lobes than Galen described, that the rete mirabile didn't exist in humans, and that the lower jaw was a single bone rather than two fused pieces. Each correction, carefully documented and illustrated, chipped away at the edifice of ancient authority. Vesalius didn't simply say Galen was wrong, he showed it, with diagrams and descriptions that anyone could verify by performing their own dissections. His description of the human skeleton was revolutionary. Earlier illustrations showed bones incorrectly proportioned or connected. Vesalius measured carefully, noted variations, and showed how bones articulated with each other. He had skeletons prepared and articulated, hung on wires so they could be studied from all angles. His skeleton illustrations are still recognizable today. You could use them to identify bones, unlike earlier anatomical drawings that were often schematic or symbolic rather than realistic. The backlash against Vesalius was fierce. Traditional physicians accused him of arrogance and error. How dare this young upstart claim that Galen, whose works had guided medicine for 14 centuries, was wrong about basic facts? Some critics suggested that human bodies must have changed since Roman times, adapting to different lifestyles. Others claimed Vesalius was simply a poor observer, seeing incorrectly or misinterpreting what he saw. His former teacher, Jacobus Silvius, wrote bitter denunciations, calling Vesalius a madman and accusing him of forging his observations. The personal attacks became so vicious that Vesalius eventually burned many of his papers in frustration and left academic medicine, becoming a court physician to Emperor Charles V and later to Philip II of Spain. It's one of the great losses of medical history. What else might he have discovered if he'd remained in research rather than being driven out by professional jealousy and resistance to change? He died in 1564, possibly in a shipwreck while returning from a pilgrimage to Jerusalem. Still in his late 40s, his greatest work behind him. But his work endured and inspired others. The floodgates were opening again. Anatomists across Europe began performing careful dissections and publishing their findings. The pace accelerated. Each generation revealed structures that had been overlooked or misunderstood. Each discovery led to questions that prompted more investigation. The culture of anatomy shifted from memorizing texts to making observations, from accepting authority to verifying claims. Gabriele Falloppio, one of Vesalius's students, described the tubes connecting the ovaries to the uterus, the fallopian tubes. He also described the structures of the inner ear with unprecedented accuracy. Bartolomeo Eustachi described the tube connecting the middle ear to the throat, the Eustachian tube, and produced detailed illustrations of the kidney that showed structures not visible in Vesalius's work. Each discovery added another piece to the puzzle of human structure, and each discoverer sought to attach their name to their findings, creating a nomenclature that mixed Latin, Greek, and eponyms in a fashion that medical students still struggle with today. The invention of the microscope in the early 17th century opened entirely new worlds within the body. Suddenly, tissue that appeared solid to the naked eye revealed intricate structure at higher magnification. Marcello Malpighi, using early microscopes in the 1660s, finally observed the capillaries that Erasistratus had inferred must exist, completing the understanding of the circulatory system. He saw them in frog lungs and bat wings, those delicate membranes where capillaries are visible as tiny vessels connecting arteries to veins. Blood actually does flow in a continuous circuit. Vessel walls are composed of distinct layers, and the barrier between blood and air in the lungs is incredibly thin. Antony van Leeuwenhoek, a Dutch draper and amateur scientist with extraordinary skill at grinding lenses, discovered blood cells, sperm cells, and bacteria, revealing that life existed at scales invisible to the naked eye. The human body wasn't just complex, it was complex at every scale of observation. Look closely enough, and tissues resolve into cells. Look closer still, and cells resolve into organelles and molecular machinery. Each level of magnification revealed new depths of organization. The discovery of cells was profound. Earlier anatomists had worked at the level of organs and tissues. Now, a new understanding emerged. All living things are composed of cells, and cells are the fundamental units of life. This insight, developed through the 19th century into what became cell theory, transformed biology and medicine. Disease could now be understood at the cellular level, some cells dividing uncontrollably in cancer, others invaded by microorganisms in infection, and others failing to function properly in metabolic disorders. William Harvey's work on blood, Circulation, published in 1628, finally overturned Galen's theory that blood was consumed by the body. Harvey demonstrated through careful observation and logical reasoning that blood must circulate continuously, pumped by the heart through the arteries, returning through the veins to be pumped again. His calculations were simple but devastating to older theories. The heart pumped about 2 ounces of blood with each beat. It beat about 70 times per minute. That meant over 500 ounces, more than 30 pounds, of blood pumped per minute. The entire body contained only about 8 or 9 pounds of blood. Within half an hour, the heart would pump more blood than the entire body weight. Clearly, blood couldn't be continuously manufactured and consumed. It had to circulate. Harvey faced his own backlash. Older physicians were outraged at this overturning of Galenic doctrine. His practice suffered as patients, hearing of his revolutionary ideas, worried he might be unreliable. But his evidence was so strong, his reasoning so clear, that within a generation, his theory was generally accepted. It helped that his predictions proved correct. Once you understood circulation, certain medical observations made more sense. The pulse in distant arteries coinciding with heartbeats, the dangers of severing particular vessels, the effects of tourniquets on blood flow, all these became comprehensible in light of circulation. This insight transformed understanding of physiology and opened new avenues for medical treatment. If blood circulates, then substances entering the blood can reach the entire body. This explained how poisons could kill after entering through a wound, how medicines taken by mouth could affect distant organs, and how diseases might spread through the body. It also suggested new possibilities. If you could introduce therapeutic substances directly into the blood, they might act more quickly and effectively than oral medications. The 18th and 19th centuries saw anatomical knowledge expand exponentially. Bodies became more readily available for dissection, legally through donations and medical school programs, and illegally through grave robbing and body snatching, a grim trade that flourished when legal supply couldn't meet demand. The expansion of medical schools created a voracious appetite for cadavers. Each school needed bodies for teaching anatomy, and with classes growing larger, the demand exceeded what executions and legitimate donations could provide. Into this gap stepped the resurrection men, as they were euphemistically called, who robbed fresh graves to supply anatomists with material. The economics were straightforward and perverse. A fresh corpse could fetch a substantial sum, enough to make grave robbing a profitable, if risky, enterprise. The resurrection men worked at night, quickly and efficiently. They'd locate a recent burial, dig down to the coffin, break it open, and extract the body, sometimes using hooks to drag it out. They typically left clothing and jewelry behind. Stealing those was robbery, a serious felony, whereas taking just the body was a lesser crime in many jurisdictions. The corpse itself had ambiguous legal status. It wasn't exactly property, so taking it wasn't technically theft in the same way. Families who could afford it took precautions. Iron cages called mort safes were placed over graves to prevent digging. Some cemeteries employed watchmen. Wealthy families built mausoleums or vaults that were harder to breach. The poor, as always, were most vulnerable. Their loved ones were buried in simple graves that resurrection men could easily raid. This created class resentment. The bodies of the poor were taken to trained doctors who would primarily serve the wealthy. The notorious Burke and Hare murders in Edinburgh revealed the dark side of medicine's hunger for knowledge. William Burke and William Hare, Irish immigrants living in Scotland, discovered they could make good money selling corpses to anatomist Robert Knox. Rather than rob graves, they simply murdered people. 16 victims in 1828 alone. They targeted the vulnerable, elderly, poor, or intoxicated people who wouldn't be quickly missed. They'd suffocate victims by sitting on their chests while covering their mouths and noses, a method that left few marks. Then they'd sell the bodies to Knox, who apparently asked no questions about their suspiciously fresh condition. The resulting public outcry when the murders were discovered led to reform, eventually establishing legal frameworks for body donation that respected both the needs of science and the dignity of the dead. The Anatomy Act of 1832 in Britain allowed unclaimed bodies from workhouses and hospitals to be used for dissection, reducing the need for grave robbing while still maintaining the troubling class dimension. It was still primarily the poor whose bodies ended up on dissection tables, but at least the system was legal and somewhat regulated, with provisions for proper burial after anatomical examination. Similar reforms occurred across Europe and America, though the transition was gradual and uneven. Medical schools began establishing relationships with hospitals and poorhouses. Donation programs were developed, allowing people to designate their bodies for medical education. The practice of using only executed criminals gradually faded, replaced by a system that, while still imperfect, at least didn't depend on crime and grave robbery. The cultural attitude toward dissection slowly shifted from horror to grudging acceptance, to, eventually, recognition that body donation was a valuable contribution to medical advancement. Modern medical students still spend countless hours in anatomy labs, though the experience is quite different from what Herophilus or Vesalius knew. Bodies are now preserved with formaldehyde or other chemicals, preventing decay and allowing for extended study. The smell is distinctive, chemical rather than organic, still unpleasant, but not the overwhelming stench of decomposition. The tissues are firmer, more leathery in texture, and coloured grey-brown by the preservatives. Blood vessels are often injected with coloured latex or plastic compounds, so they stand out, making them easier to trace and identify. Dissection proceeds slowly over months, with detailed instruction and careful documentation. Students work in small groups, each group with their own cadaver. They follow a systematic sequence, starting with the back and limbs, progressing to the thorax and abdomen, and finally reaching the head and neck. Each session focuses on specific structures. The students read ahead, studying what they'll encounter, then carefully dissect to reveal those structures, identify them, and understand their relationships to surrounding tissues. Students name every structure they uncover, learning not just gross anatomy but also the relationships between organs, the pathways of vessels and nerves, and the variations that make each body unique. And the variations are striking. Arteries don't always follow the textbook pattern. Some people have extra muscles or missing muscles. Organs vary in size and position. Each body teaches slightly different lessons, preparing students for the variability they'll encounter in living patients. The relationship between students and their cadaver is complex and profound. Many anatomy labs hold brief ceremonies at the beginning and end of the course, acknowledging the gift that donors have given. Students often develop deep respect for their cadaver, referring to them with affection and gratitude. They know the person's age, often their cause of death. They sometimes name them, trying to maintain some sense of the personhood that inhabited this form. It's an intimate experience, literally getting inside another person's body, seeing structures no living person can see in themselves, and holding organs that sustained a life. This intimacy can be emotionally challenging. The first cut is difficult for most students. There's a barrier to overcome, a natural reluctance to damage a human body. Some students struggle with the reality of working with the dead, especially when they reach the face. It's easier to maintain clinical distance when dissecting an arm or abdomen. The face is different. Features remain recognizable. Individuality persists. This is clearly someone who smiled, spoke, and looked at the world. Dissecting the face, removing muscles layer by layer, sawing through the skull to access the brain, these procedures require students to navigate complex emotions about mortality, identity, and the transformation of person into specimen. Yet many anatomists argue that there's something irreplaceable about actual dissection, about working with real human tissue, discovering the variations and surprises that every body contains. Textbooks and digital models show idealized anatomy, but real bodies are delightfully irregular. Arteries follow slightly different paths. Muscles have unusual attachments. Organs vary in size and position. These variations matter in clinical practice, and students need to expect them rather than assuming everyone matches the textbook diagram perfectly. A surgeon opening an abdomen needs to be prepared for anatomical variance. Finding, for instance, that the appendix is positioned unusually, or that blood vessels branch differently than expected. Technology is beginning to supplement traditional dissection with virtual and augmented reality systems, 3D printed anatomical models, and detailed digital scans. These tools can show structures from any angle, let students dissect and reassemble organs repeatedly, reveal microscopic details, and demonstrate physiological processes in real time. They're valuable additions to medical education, expanding what's possible to teach and learn. You can show blood flowing through vessels in real-time simulation, demonstrate how muscles contract and relax, and zoom in from gross anatomy to cellular structure seamlessly. Some programs now offer virtual dissection tables, large touchscreens, displaying highly detailed 3D anatomical models. Students can peel away layers, rotate structures, and highlight specific systems. They can switch between male and female anatomy, see pediatric variations, and examine pathological specimens. These tools are especially useful for rare conditions or dangerous procedures that students might not encounter in their limited cadaver experiences. You can demonstrate what happens in an aortic dissection or a traumatic brain injury without needing actual specimens of these conditions. There's also something profound about the responsibility and intimacy of dissection. You're not interacting with a digital model or a plastic replica. You're being trusted with someone's actual body, their physical remains. That person lived, loved, laughed, suffered, and died, and now they're teaching you. The experience tends to instill humility and respect, reminding medical students that their future patients will be real people with real bodies, not abstract cases or diagnostic puzzles. The cadaver is the student's first patient, one who can no longer speak but still has much to teach. The ethical questions that troubled Alexandria haven't entirely disappeared. They've evolved. We still debate the proper treatment of the dead, though in different terms. We discuss informed consent and body donation procedures, ensuring that people who donate their bodies understand what will happen to them, that their wishes are documented clearly, and that their remains are treated with respect throughout the educational process. Most programs now have policies requiring that bodies be used only for education and research, that photography be restricted, and that students maintain professional conduct at all times. We wrestle with questions about what experiments are acceptable on human tissue, whether from cadavers or living donors. Is it acceptable to practice surgical techniques on donated bodies? Most would say yes, if it improves surgical skill and ultimately saves lives. What about testing new medical devices or procedures? The ethical calculation becomes more complex. What about plastination for public display, as in the Body World's exhibitions? Opinion is divided, even among ethicists and anatomists. We consider how to balance the needs of medical research with cultural and religious values that may view dissection differently. Different cultures have different comfort levels with these practices. Some religious traditions explicitly support body donation as a final act of charity. In Buddhism, for instance, the body after death is often considered an empty vessel, and using it to benefit others through medical education is seen as meritorious. Some forms of Christianity similarly emphasize that the body is temporary, that the soul has departed, and that using remains to help the living is an act of love. Others prefer that bodies remain intact when possible, though they may allow exceptions. When the knowledge gained could save lives, Islamic law generally requires burial within a day of death and views the body as sacred, making dissection problematic, though some modern Islamic scholars have argued that medical education constitutes sufficient necessity to permit it. Orthodox Judaism traditionally opposes dissection, but has grappled with exceptions. Some authorities permit it when the knowledge directly benefits an identifiable patient needing that specific procedure. Native American communities have complex and varied traditions about handling the dead, often emphasizing the need to keep the body whole and return it to the earth. Many Native people view dissection as a profound violation, though some communities have developed their own approaches to medical education that honor both traditional values and the need for Native physicians. The conversation continues, evolving as society evolves, trying to find balance between competing goods, advancing medical knowledge versus respecting cultural traditions, benefiting future patients versus honouring the dead. One fascinating development is the emergence of body donation for public education, not just medical training. The Body Worlds exhibitions, which display plastinated human bodies in various poses and dissections, have been viewed by millions of people worldwide. Plastination, developed by Gunther von Hagens, is a preservation technique that replaces water and fat in tissues with plastics, creating specimens that are dry, odourless, and durable. The bodies remain remarkably lifelike in texture and detail, while requiring no refrigeration or special care. These exhibits are controversial. Some see them as educational and demystifying, making anatomical knowledge accessible to the public in ways that textbooks and diagrams never could. Walking through a Body Worlds exhibition, you can see actual human muscles, observe how they attach to bones, follow blood vessels through their intricate pathways, and examine diseased organs alongside healthy ones. It's undeniably educational. Children and adults alike come away with new understanding of their bodies, often reporting that they're motivated to make healthier choices after seeing what smoking does to lungs or obesity does to joints. Others view these exhibitions as disrespectful or sensationalist, posing bodies in artistic or athletic positions, a plastinated body kicking a soccer ball, for instance, or posed in a dancer's arabesque, strikes some observers as treating human remains as entertainment rather than education. There are questions about consent. Did the donors fully understand that their bodies would be displayed publicly, posed in specific ways, and viewed by millions? The exhibitions claim that all specimens come from voluntary donors who signed detailed consent forms, but verification is difficult. The exhibits also raise questions about dignity and commodification. Is displaying plastinated bodies fundamentally different from displaying them in medical museums, where specimens have been kept for centuries? What about charging admission? Does that commodify human remains? These questions don't have easy answers. The ethics depend partly on intent, partly on execution, and partly on individual and cultural values about what constitutes respectful treatment of the dead. This democratization of anatomical knowledge has interesting effects. People who've seen real human anatomy often report a new appreciation for their bodies and health. The abstract advice to eat well and exercise becomes more concrete when you've seen actual arteries clogged with fatty deposits or actual lungs damaged by smoking. The tarry, blackened appearance of a smoker's lungs compared to healthy pink tissue is viscerally convincing in a way that statistics about cancer risk may not be. Similarly, seeing the worn cartilage in an arthritic joint or the enlarged, struggling heart of someone who is obese makes the consequences of lifestyle choices tangible. The body stops being a mysterious black box and becomes something you understand, at least basically, empowering you to make more informed decisions about your health. You realize that your skeleton is supporting you right now, that your heart is beating, that your lungs are exchanging gases, that your liver is processing substances, and that your kidneys are filtering blood. These aren't abstract processes, but physical realities happening in specific structures you could theoretically see and touch. We're also in an era where individuals can access their own anatomical data in unprecedented detail. If you have an MRI or CT scan, you can request copies of the images and explore them, seeing your own internal structure with your own eyes. The images are stored digitally, often with viewer software that lets you scroll through slices of your body, zoom in on structures, and adjust contrast to highlight different tissues. You can see your own brain, observe how it fills your skull, note the ventricles that Herophilus described, and trace your own arteries as they branch and divide. Some radiologists are creating 3D printed models of patients' anatomy for surgical planning, essentially giving people physical representations of their own organs and bones. A patient with a complex bone fracture might receive a 3D printed model of their actual bones, showing exactly where the break occurred, allowing them to understand the injury and the planned repair much more clearly than any verbal description could convey. Surgeons use these models to plan approaches, practice difficult cuts, and anticipate challenges before they open the patient. This technology turns everyone into something of an anatomist, exploring not just generic human anatomy, but their own unique variation. You might discover that your sinuses are shaped differently than textbook diagrams, or that you have an anatomical variant that's rare but harmless, perhaps an extra rib or an unusual blood vessel course. This personal anatomical knowledge can be empowering, helping you communicate more effectively with healthcare providers and understand your own medical conditions better. Looking back across the 23 centuries since Herophilus made his first cuts, the progress is staggering. We've gone from knowing almost nothing about internal anatomy to being able to image living bodies in exquisite detail, to perform incredibly sophisticated surgeries, to understand disease at the molecular level. We've mapped every organ system, traced every major vessel and nerve, and catalogued thousands of variations and abnormalities. We've extended human lifespan dramatically, reduced mortality from countless diseases, and improved quality of life for billions of people. Consider what surgery was like before anatomical knowledge. Procedures were limited to external injuries, amputations, and perhaps some abdominal operations done essentially blind, with the surgeon having only vague ideas of what they'd encounter. The mortality rate was appalling, not just from surgical trauma, but from infection, bleeding, and organ damage. Modern surgery depends absolutely on anatomical knowledge. A cardiac surgeon must know precisely where coronary arteries run to perform bypass grafting. A neurosurgeon needs detailed understanding of brain structure to remove tumours without damaging critical areas. An orthopedic surgeon must understand how bones, ligaments, and muscles interact to successfully repair joints. The development of anaesthesia in the mid-19th century made surgery bearable for patients, but it was anatomical knowledge that made surgery effective. You could put a patient to sleep, but if you didn't know where to cut, what to remove, how to repair, or what to avoid, sleep merely meant the patient died without pain rather than in agony. The combination of anatomy, anaesthesia, and antiseptic technique, the germ theory that explained infection, transformed surgery from a desperate last resort to a powerful therapeutic tool. Yet for all we've learned, mysteries remain. The brain still guards many secrets about consciousness, memory, and personality. We can map its structures, trace its connections, measure its electrical activity, and identify regions associated with specific functions. We know that damage to certain areas causes specific deficits, but we still don't fully understand how neural activity produces subjective experience, how memories are stored and retrieved, why personalities differ, or what exactly happens during sleep and dreaming. The anatomical substrate is clear enough, but the emergence of mind from matter remains profoundly mysterious. The immune system's complexity still surprises researchers. We know it involves multiple types of cells, intricate signaling molecules, and sophisticated mechanisms for distinguishing self from non-self. We've learned to manipulate it with vaccines and immunotherapies, but autoimmune diseases, where the system attacks the body's own tissues, remain puzzling. Why does the immune system sometimes mistake body tissues for threats? Why do these diseases often affect women more than men? Why do they cluster in certain families? The answers are emerging slowly, piece by piece, but complete understanding remains elusive. The microbiome, the trillions of bacteria living in and on our bodies, is only beginning to be understood. We're not really individual organisms, but ecosystems, hosting communities of microbes that affect digestion, immune function, and possibly even mood and behavior. Disrupting these communities with antibiotics or poor diet can have far-reaching consequences. Supporting them with appropriate nutrition and avoiding unnecessary antimicrobials promotes health. This realization is transforming our understanding of what a human being is. We're not just the cells with our DNA, but the entire ecosystem, human cells and microbial cells together, in complex symbiosis. Chronic pain, autoimmune diseases, and many neurological conditions still puzzle us. We can describe what happens: nerves sending pain signals without apparent cause, immune cells attacking joints or other tissues, neurons dying in Parkinson's disease, or multiplying abnormally in epilepsy. But the deeper questions of why these processes go wrong in some people and not others, how to prevent them, and how to reliably correct them, these remain areas of active research with incomplete answers. Medicine has made remarkable progress, but humility is appropriate. We know much, but much more remains unknown. Cancer, that collection of diseases where our own cells turn against us, continues to be a formidable challenge despite enormous progress. We understand cancer much better now than even a generation ago. We know it involves mutations that cause cells to divide uncontrollably, evade growth suppressors, resist death signals, induce blood vessel formation, invade tissues, and metastasize to distant sites. We've developed targeted therapies that attack specific mutations, immunotherapies that harness the patient's immune system, refined surgical techniques, more precise radiation methods, and more. Survival rates for many cancers have improved dramatically. Yet cancer remains deadly, claiming hundreds of thousands of lives annually in the United States alone. Some cancers remain stubbornly difficult to treat: pancreatic cancer, glioblastoma, and certain lung cancers. Others respond well to treatment initially, but develop resistance, evolving to evade therapies. Cancer cells are our own cells gone rogue, sharing most of their characteristics with normal cells, making it difficult to kill them without harming healthy tissue. It's an evolutionary battle, with the cancer evolving to survive treatment and medicine evolving new approaches to combat resistance. Each answer we find seems to reveal new questions. When Herophilus first traced nerves to the brain, he couldn't have imagined neurons, synapses, neurotransmitters, or brain waves. When he described the ventricles and their cerebrospinal fluid, he couldn't have known about the blood-brain barrier, about how this fluid cushions the brain, or about how it's produced and circulates. When Vesalius corrected Galen's errors, he had no concept of cells, let alone DNA, proteins, or the molecular machinery of life. Each generation of anatomists and physiologists pushed deeper, revealing new layers of complexity, and there's no reason to think we've reached the bottom. There may be no bottom. Complexity may extend in both directions, smaller and larger, simpler and more intricate forever. Below cells are organelles, below those are molecules, below those are atoms, and below those are subatomic particles and quantum fields. Above cells are tissues, above those are organs, above those are systems, above those is the integrated organism, and even above that are populations, ecosystems, and the biosphere. At each level, new properties emerge that can't be simply predicted from the level below. A neuron has properties that atoms don't. A brain has properties that neurons don't. A person has properties that a brain doesn't. And societies have properties that individuals don't. But this shouldn't discourage us. The journey of discovery, not just the destination, has value. Each insight we gain helps us understand ourselves better, treat diseases more effectively, and appreciate the magnificent machinery we inhabit. And perhaps, in continuing this work, we honour those first pioneers who had the courage to look beneath the skin, to question ancient authorities, and to insist that knowledge was worth pursuing, even when it required overcoming powerful taboos. Thinking about Herophilus for a moment, that young physician in Alexandria, with his questions and his scalpel, He couldn't have known that his work would echo through millennia, that his names for anatomical structures would persist into an age he couldn't imagine, and that medical students in the 21st century would still learn about the torcular, hierophily. He was solving immediate problems, answering pressing questions, and trying to understand the body so he could better heal the sick. The long-term implications, the philosophical transformations, the eventual triumph of observation over authority, these weren't his goals. He just wanted to know what was there. Yet his simple decision to look, to verify, to document what he actually saw rather than what authority claimed he should see, initiated a revolution. Not all at once. The revolution faltered, stopped, restarted centuries later, faced fierce opposition and advanced haltingly, but the principle he established survived. Observation trumps authority. Seeing is more reliable than supposing, and the human body is knowable through systematic investigation rather than mystical speculation or pure reason. This principle extended far beyond anatomy. The scientific revolution that transformed humanity's understanding of the natural world rested on this foundation: the insistence that nature must be observed, that experiments must be performed, and that theories must conform to evidence rather than evidence conforming to theories. Galileo pointing his telescope at Jupiter and seeing moons in orbit, thereby proving that not everything orbited Earth, was following Herophilus's example. Darwin observing finches and fossils and deriving the theory of evolution was doing the same. Every scientific advance depends on this willingness to look carefully at reality and report what's actually there, regardless of what tradition, authority, or preference might suggest. As you lie here, approaching sleep, consider your own body with fresh appreciation. Every breath you take involves dozens of muscles working in coordination. Your diaphragm contracts, flattening downward and expanding your chest cavity. Your external intercostals contract, lifting your ribs upward and outward. The pressure inside your chest decreases and air rushes in through your nose or mouth, down your trachea and into bronchi and bronchioles, finally reaching the microscopic alveoli where oxygen diffuses into your blood and carbon dioxide diffuses out. Then your diaphragm and intercostals relax, your chest cavity decreases in volume and air flows out. This cycle repeats about 15 times per minute, all day, all night, from birth to death, usually without conscious thought. Your heart continues its tireless work, pushing blood through thousands of miles of vessels. Each heartbeat involves a precisely choreographed sequence. Electrical signals originate in the sinoatrial node, your heart's natural pacemaker, and spread through the atria, causing them to contract and push blood into the ventricles. The signal pauses briefly at the atrioventricular node, giving the atria time to finish contracting, then spreads rapidly through the ventricles via specialized conducting fibers, causing them to contract from bottom to top, efficiently ejecting blood into the pulmonary artery and aorta. Valves snap shut, preventing backflow, creating the familiar lub-dub sound. The whole cycle takes less than a second, and then it repeats. Your digestive system processes whatever you ate today, breaking it down and extracting nutrients. In your stomach, acid and enzymes are breaking proteins into smaller peptides. In your small intestine, more enzymes and bile are breaking down fats and carbohydrates and completing protein digestion. Nutrients are being absorbed through the intestinal wall into blood vessels that carry them to your liver for processing. Your large intestine is absorbing water and housing the bacteria that help digest fiber and synthesize certain vitamins. Waste is being compacted for eventual elimination. All of this happens automatically, regulated by nerves and hormones, requiring no conscious oversight. Your immune system patrols constantly, identifying and eliminating threats. White blood cells circulate through your bloodstream and patrol your tissues, sampling their environment and checking molecular signatures on cells they encounter. Most of the time, they find only self cells and molecules that belong, but occasionally they detect something foreign, a virus, bacteria, or abnormal cell. The immune response kicks in, a cascade of events involving multiple cell types, chemical signals, antibodies, and inflammation. Most infections are cleared without you even noticing. You only become aware when the infection is large enough that the immune response itself causes symptoms: fever, inflammation, and fatigue. Your nervous system monitors countless sensations, most of which never reach your conscious awareness because they're handled automatically. Receptors in your skin are constantly reporting pressure, temperature, and position. Receptors in your muscles and joints are monitoring tension and angle. Receptors in your organs are tracking blood pressure, oxygen levels, stomach fullness, and bladder distension. Most of this information is processed by your spinal cord and brainstem without bothering your conscious mind. Only novel, important, or dangerous sensations break through to awareness. Right now, unless I draw your attention to it, you probably aren't aware of the pressure of your body against the bed, the temperature of the air, or the ambient sounds around you. Your nervous system was monitoring them, but not troubling your consciousness with the details. Your endocrine system releases precisely measured doses of hormones, adjusting your metabolism, growth, and reproduction. Your thyroid is releasing hormones that regulate how fast your cells burn fuel. Your adrenal glands are releasing cortisol in a daily rhythm, high in the morning to help you wake and lower at night to let you sleep. If you ate recently, your pancreas released insulin to help cells absorb glucose from your blood. If it's been a while since you ate, your pancreas is releasing glucagon to signal your liver to release stored glucose. If you're stressed, your adrenals release adrenaline, preparing you for action. These hormones circulate in your blood, reaching every cell, binding to specific receptors, and adjusting cellular behavior in coordinated ways. All of this happens without your conscious direction, managed by systems so complex and interconnected that no computer we've built comes close to matching their sophistication. Yet it all runs on the energy from food, powered by chemical reactions, following physical laws, operating according to principles we can observe and understand. The mystery isn't separate from the mechanism. The mystery is in how something so mechanical can produce consciousness, personality, creativity, love, and the sense of being you, experiencing this moment right now. Herophilus couldn't have known where his first cut would lead, how his courage to observe would spawn a tradition lasting millennia, how his questions would eventually illuminate not just the structure, but the function of the human body, and even begin to address those deepest questions of what we are and how we work. He simply wanted to know what was there, underneath the skin, in the space between the external appearance we show the world and the internal reality that keeps us alive. That impulse to know, to understand, to see what's really there rather than what we assume or hope or fear is there, remains at the heart of all science and medicine. It's an impulse worth honoring, worth continuing, and worth supporting. Each of us benefits from the knowledge gained through centuries of anatomical study, from the surgical techniques to the diagnostic procedures to the basic understanding of health and disease that shapes how we live our lives. The story of dissection is ultimately a story of courage overcoming fear, curiosity overcoming taboo, and knowledge overcoming superstition. It required brave individuals willing to challenge norms, authorities willing to permit controversial practices, and families willing to trust that this strange act of cutting open the dead would ultimately benefit the living. It required generation after generation of anatomists, each adding pieces to the puzzle, correcting errors, revealing new details, and passing their knowledge forward. Consider the chain of transmission. Herophilus taught students in Alexandria. Those students preserved his work in manuscripts, though most were eventually lost. Later physicians read those manuscripts and built on them. Galen synthesized ancient knowledge and added his own observations, though he couldn't dissect humans. Medieval scholars preserved Galen's works through centuries when new dissection was impossible. Renaissance anatomists rediscovered human dissection and corrected Galen's errors. Each generation stood on the shoulders of previous ones, seeing a little farther, understanding a little more deeply. We are the current link in that chain. The anatomical knowledge you use, when you understand that chest pain might indicate a heart problem, when you know that a blow to the head can be dangerous even without external injury, when you make choices to protect your lungs or liver or joints, rests on centuries of accumulated observation. When a surgeon operates on you or someone you love, they're using knowledge and techniques refined over generations, all ultimately tracing back to those first courageous cuts in Alexandria. And the chain continues forward. Medical students today are making observations, noticing variations, and learning techniques. Researchers are using anatomical knowledge as a foundation for understanding disease and developing treatments. New imaging technologies reveal structures with unprecedented detail. Genetic information is being integrated with anatomical understanding, explaining why some people have anatomical variants and why some are more susceptible to certain diseases. The story isn't finished. It may never be finished. Each answer generates new questions. Each technique enables new discoveries, and each generation pushes understanding deeper. So tonight, as you drift towards sleep, you carry with you a lineage of discovery stretching back through the centuries. You are the inheritor of knowledge gained through courage, curiosity, and countless hours of painstaking observation. You are also yourself a marvel, a living, breathing, thinking example of the very anatomy those ancient pioneers first dared to explore. The body you inhabit is both the object of study and the instrument of understanding, both the question and, in some sense, the answer. Rest well, knowing that the journey from that first blade in Alexandria to modern medicine is a story of human courage and curiosity at their finest. Sleep comes naturally to a body that knows itself, that trusts in the billions of years of evolution that have shaped its systems, and that exists in the long tradition of inquiry and understanding that began when someone first dared to look inside and really see what makes us human. Your body will continue its work as you sleep. Heart beating, lungs breathing, cells dividing and dying, proteins being synthesized, waste being processed, and memories being consolidated in your brain. All the systems Herophilus and his successors revealed will carry on their ancient functions, keeping you alive, sustaining consciousness, and making possible the miracle of another day. And in the morning, you'll wake, and all these systems will shift into higher gear, preparing you for activity, supporting your movement and thought, and enabling you to engage with the world. You'll do this without thinking about the anatomy that makes it possible, just as people did for millennia before anyone looked beneath the skin. But now, having walked through this history together, perhaps you'll carry some awareness of the gift those early anatomists gave us. The gift of understanding, of knowledge wrested from ignorance and taboo, of science triumphing over superstition to reveal the magnificent machinery that we are. The first dissection happened 23 centuries ago, but its echoes continue. Every time we learn something new about the human body, every time a student encounters anatomy for the first time, and every time a patient benefits from anatomical knowledge, that first cut in Alexandria reverberates. Herophilus reached across time, his questions our questions, his courage inspiring ours, and his dedication to understanding what we truly are, rather than what we wished or feared. We were establishing a precedent we still follow. May we prove worthy inheritors of that tradition, continuing the great work of understanding ourselves. for as long as humans remain curious about the mystery of our own being. Sleep well. Tonight, guys, we're going to learn about the nervous system, but not in the crazy electric way you might think. Instead, we'll learn how this amazing network... Tonight, guys, we're going to learn about the nervous system, but not in the crazy electric way you might think. Instead, we'll learn how this amazing network of cells and pathways makes the most peaceful times in your life. We'll walk together through the quiet hallways of your brain as it gets ready for sleep. We'll meet the soft chemical messengers that guide you to sleep and learn how your body's most complicated system becomes your most trusted friend in sleep. Instead of seeing your nervous system as a buzzing electrical grid, picture it as a huge old library that is closing. The day's busy readers have left. The harsh fluorescent lights have dimmed to warm amber, and now the sacred ritual of organizing, filing away, and getting ready for tomorrow's discoveries begins. Tonight we'll look at the nervous system that gently guides you into sleep, not the one that wakes you up with morning alarms. Let's start our journey in the place we know best, your brain, which is a 3-pound universe that lives safely inside your skull. But tonight, we won't think of it as your body's command center barking orders. Instead, think of it as an old, wise conductor getting an orchestra ready for its last and most beautiful movement of the day. Your neurons are like musicians getting ready to play the most relaxing symphony ever written, the music of sleep. You see, your brain isn't just one organ, it's made up of different neighborhoods, each with its own personality and job. As night falls, these neighborhoods slowly change from the busy activity of day to the calm rhythms of night. The cerebral cortex, the wrinkled outer layer of your brain where your conscious thoughts dance when you're awake, starts to calm down. The millions of neurons that spent the day processing information, making decisions, and making memories now start to slow down, like streetlights going out one by one across a city at midnight. This change doesn't happen all at once like flipping a switch. Instead, it happens slowly, like a sunset, with colors changing from bright gold to soft amber to deep purple without anyone noticing. Your cortex has different parts that need to wind down at different times this evening. The visual cortex, which worked hard all day to make sense of the stream of images coming in through your eyes, starts to let go of the outside world first. The auditory regions, which processed every sound from birds singing in the morning to people talking at night, begin to ignore the less important sounds of everyday life. But this quieting isn't random or out of control. It follows patterns that are written into your DNA and have been guiding human sleep for hundreds of thousands of years. The suprachiasmatic nucleus is a small group of cells deep in your brain that acts as your body's master clock. Imagine a patient old lighthouse keeper looking out over the water for signs of darkness, ready to start the evening's gentle ritual of guiding ships safely to port. This amazing timepiece, which is only as big as a grain of rice, has about 20,000 neurons that pulse in time with the rotation of the Earth. These cells get messages from your eyes about how bright the world is during the day. But when night falls, they start to put together the most complicated biological symphony you'll ever hear. The change from being awake to being asleep. The suprachiasmatic nucleus doesn't do this by itself. It works with other timing centers in your body to make what scientists call a hierarchy of biological clocks. Every organ, tissue, and even single cell has its own rhythm. Your liver has its own clock that helps it break down nutrients. Your muscles have clocks that tell them when to grow and fix themselves. Your immune system has clocks that tell it when to be most careful about getting sick. All of these peripheral timekeepers look to your suprachiasmatic nucleus as their conductor, following its lead as it responds to the daily cycle of light and darkness. The first movement of this symphony starts with the slow lowering of a hormone you might not expect, cortisol. Cortisol is a gentle motivator during the day that helps you stay alert and focused. It naturally rises in the morning, giving you the energy you need to face the day's challenges. It also naturally ebbs and flows depending on how stressed or active you are, but when your master clock knows that night is coming, It tells your adrenal glands to make less cortisol. Imagine the conductor's baton slowly lowering, telling the brass section to stop playing. This suppression of cortisol is very important because cortisol and sleep are very closely linked. Having too much cortisol in your blood will keep you awake and anxious, with your mind racing with thoughts and your body tense and ready to act. When cortisol levels drop in the evening, your nervous system gets one of its first signals that it's time to switch from the active mode of day to the restorative mode of night. A small, pinecone-shaped gland in the center of your brain, called the pineal, starts its nightly routine at the same time. The pineal gland is one of the most beautiful parts of the human body. Philosophers used to call it the seat of the soul, but we now know it as the source of something just as magical, melatonin. The pineal gland is located between the two hemispheres of your brain. It is connected to your visual system through a complicated pathway that lets it detect changes in light, even though it is deep inside your skull. When it gets dark, this tiny gland starts to release melatonin into your bloodstream, like a soft mist spreading over a calm lake at dusk. Melatonin levels stay low during the day and start to rise as evening approaches. This is a pattern that happens every time. The most production happens in the middle of the night, usually between 2 and 4 a.m. After that, it slowly goes down until dawn. A lot of people think that melatonin is a sleeping pill that your body makes, but it's not. It's more like a soft whisper, a chemical lullaby that travels through your blood to receptors all over your nervous system. When melatonin touches these receptors, they start to change how your brain works from the bright, sharp focus of the day to the soft, flowing rhythms of sleep. Melatonin doesn't make you sleep. It just opens the door and gently asks you to come in. There aren't equal amounts of melatonin receptors in your brain. They group together in places that are important for controlling sleep, especially in the suprachiasmatic nucleus itself. This creates a feedback loop in which melatonin affects the master clock that starts melatonin production. This helps to stabilize and strengthen your circadian rhythms. It's like a grandfather clock that not only tells time, but also listens to its own ticking to make sure it stays in perfect time. But getting ready for sleep isn't just about turning off systems that are active during the day. It also needs to gently wake up sleep-promoting pathways that have been patiently waiting their turn. Clusters of neurons in a part of the brain called the ventrolateral preoptic area, which we'll call the sleep center, start to release a chemical called GABA. Melatonin is a soft whisper at night, while GABA is a warm hug. Gamma-aminobutyric acid, or GABA, is the main neurotransmitter that stops your nervous system from working. In other words, it's the chemical that tells other neurons to slow down, talk more quietly, and get into a calmer rhythm. Think of GABA as a kind librarian who walks through the stacks at closing time and puts a finger to her lips to tell everyone to be quiet. Your sleep center's neurons don't just release GABA at random times. They make a complex network that can feel how your brain and body are doing and react to signals about your stress levels, fatigue, circadian time, and even your mood. When these neurons that help you sleep sense that it's time to rest, they start to work harder and send out waves of GABA that spread through your nervous system like ripples on a pond. As GABA spreads its calming effect through your brain, something wonderful starts to happen in your cerebral cortex. The beta waves that made your mind alert and thinking start to slow down and change into alpha waves. The brain's alpha waves are like a deep, satisfied sigh. They stand for that calm time between waking up and going to sleep, when your mind is still aware, but not actively trying to think or solve problems. This change from beta to alpha waves is a big change in how your brain processes information. When beta waves are in charge, your neurons fire in patterns that are mostly independent and happen at a high frequency. This helps with focused attention, analytical thinking, and active problem solving. But when alpha waves start to appear, your neurons start to work together, firing in longer, slower rhythms that help you relax and think about yourself. When your brain switches to alpha waves, the activity in its network also changes. When you are awake and alert, your brain keeps what neuroscientists call task-positive networks. These are groups of brain areas that work together to focus your attention on the outside world and help you reach your goals. But as alpha waves get stronger, these task-positive networks start to quiet down, and other networks become more important. The default mode network is one of the most important networks that comes to life when you relax. When your mind isn't focused on anything in particular, like when you're mentally wandering, this network becomes active. The default mode network is linked to self-reflection, memory consolidation, and the kind of loose associative thinking that often happens before you go to sleep. This change isn't sudden, like flipping a switch. It's more like how daylight slowly fades into twilight. Your neurons, which may have been firing 30 or 40 times a second when you were really focused, are now firing at a slower pace. They start to sync up with each other, making waves of electrical activity that move across your brain like gentle swells on a calm ocean. As this synchronization gets stronger, your brain waves slow down even more, going into theta rhythms. Theta waves, which happen 4 to 8 times a second, are linked to the sleepy state just before sleep, when the edges of reality start to blur and the first wisps of dreams start to form. Your thoughts become less straight and more connected. The logical connections that guided your thoughts throughout the day yield to the more fluid and imaginative connections that will soon blossom into dreams. Theta waves are interesting because they show a state of consciousness that is not fully awake or fully asleep. When you're in this theta state, your mind is more open to making strange connections and getting creative ideas. A lot of artists and inventors say that their best ideas come to them when they are sleepy and in a theta state, either right before they go to bed or right after they wake up. Your logical and critical thinking systems have let their guard down, letting more fun and creative neural processes come to the surface. Your thalamus, which is an egg-shaped structure deep in your brain that acts as a relay station for sensory information, starts to change in one of the most amazing ways in all of neuroscience during this time. Your thalamus has been busy all day taking in information from your senses and deciding which ones you should pay attention to. Like a skilled air traffic controller, it has been able to handle the constant flow of sights, sounds, smells, and feelings that want your attention. Not only does the thalamus pass on sensory information, but it also actively sorts and prioritizes it based on what you need and what you're paying attention to right now. Your thalamus helps you focus on your friend's voice and block out the noise around you when you're talking in a busy restaurant. It makes visual signals that could be key-like objects more clear, while making other visual input less clear when you're looking for your keys. One of the most important things that consciousness does is this selective attention process. But when it's time to sleep, your thalamus starts to close the gates. It begins to block out more and more sensory information from the outside world. Sleep researchers call this sensory gating. For example, the sounds of traffic outside your window become background noise. You stop being aware of how the sheets feel against your skin. You won't notice the small changes in the temperature of the room that happen during the day. The thalamus isn't shutting down. It's just switching from connecting you to the outside world to keeping you from being disturbed while you sleep. Your nervous system does this sensory gating for you, and it's one of the most caring things it does. It knows that sleep isn't just the lack of wakefulness, it's a different state of mind that needs its own special environment. Your thalamus is like a loyal guardian that stands watch at the gates of awareness and makes sure that only the most important signals, like a crying child, a smoke alarm, or the touch of a loved one, can get through to your peaceful sleep. The thalamus does this by changing the electrical properties of its neurons, which lets some signals through and blocks others. Thalamic neurons fire in a steady, rhythmic pattern called tonic firing when you are awake. This lets them send sensory information to the cortex accurately. But when sleep is near, these neurons change to a firing pattern called burst firing, in which they go from being very active to being very quiet. This burst firing pattern works like a filter that keeps most sensory information from getting to your cortex, but lets through signals that are very important or strong. It's like having a high-tech security system that can tell the difference between a leaf falling on the roof and someone trying to break in. When you first fall asleep, the thalamus is very picky about what information it thinks is worth your time. As your brain gets deeper into this safe state, other parts of it start to get ready for sleep in their own special ways. Your brainstem, which is the oldest part of your nervous system and controls basic life functions like breathing and heart rate, starts to coordinate the physical changes that happen when you fall asleep. Neurons in the brainstem release chemicals that start to calm your muscles, slow your breathing, and lower your heart rate. The locus coeruleus is a part of the brainstem that is very important for sleep. It is also the main source of the neurotransmitter norepinephrine. Norepinephrine keeps you alert and ready to deal with problems or opportunities while you are awake. During the day, the neurons in the locus coeruleus fire all the time, releasing norepinephrine that keeps you awake. But as bedtime gets closer, something amazing happens. The locus coeruleus starts to calm down. The neurons that have been firing all day start to calm down, and the norepinephrine levels in your brain start to go down. This drop in norepinephrine is like taking away one of the main supports for your waking consciousness. It lets your brain settle into the different neural patterns that help you sleep. When the locus coeruleus calms down, it affects your whole nervous system. Norepinephrine usually helps with memory, attention, and emotional responses. Your ability to stay focused naturally decreases as its levels drop. Your feelings become less intense and more dreamy. The strong mental focus that comes with being awake starts to fade and blur around the edges. The Rafe nuclei are another important part of the brainstem for sleep. They make most of the serotonin in your brain. People often think of serotonin as a feel-good neurotransmitter, but it has a more complicated role in sleep. Serotonin helps keep your mood stable and supports different parts of your thinking during the day. But like norepinephrine, serotonin levels go down as sleep gets closer, which helps calm down the brain systems that keep us awake. When norepinephrine and serotonin levels go down, it makes room for other neurotransmitter systems to become more important. As these chemicals that help you stay awake go away, systems that help you sleep become more powerful. The GABA system we talked about before takes over and spreads its calming effect throughout the brain. When you're awake, adenosine, a chemical that builds up in the brain as a result of neural activity, reaches levels that make you sleepy and sleepy. Adenosine is especially interesting because it's how your brain keeps track of how long you've been awake. Your neurons use a molecule called ATP to get energy throughout the day as they work to process information and stay awake. Adenosine is one of the things that comes out when ATP is broken down to free its energy. Your brain builds up more adenosine the longer you stay awake. Sleep researchers call the rising levels of adenosine sleep pressure. This is a biological urge to sleep that gets stronger over time. Adenosine works on certain receptors in your brain that make you sleepy and slow down systems that keep you awake. This is why you get more and more tired as the day goes on, even if you don't do anything physical. Your brain is literally keeping track of how long you've been awake and slowly increasing the pressure to rest and get better. Caffeine works by blocking adenosine receptors, which stops adenosine from making you sleepy. This is why caffeine can make you feel awake even when you haven't had enough sleep. It doesn't give you energy, it just stops your brain from getting the signals that tell it to rest. When the caffeine wears off, all the adenosine that has built up hits your adenosine receptors at once. This is what causes the caffeine crash that many people feel. As your brain gets into this sleep-friendly neurochemical state, high GABA and adenosine, low norepinephrine and serotonin, the real magic of sleep starts to happen. Your neurons, which spent the day making connections and remembering things, are now doing the important work of consolidation and maintenance. It's like the brain's nightly cleaning routine, but instead of cleaning furniture and putting things away in closets, your neurons are strengthening important memories and getting rid of the metabolic waste that built up while you were awake. Scientists poetically call this process synaptic scaling, or synaptic homeostasis. As you learn new things and have new experiences throughout the day, the connections between your neurons, which are called synapses, get stronger. Memories are made, and knowledge grows when synaptic connections get stronger. Every time you practice a skill or remember something, the neural pathway gets stronger and works better. But if this kept going on without stopping, your brain would eventually get full, like a hard drive that has no space left for new files. The synapses would get so strong and so many that they would get in each other's way, making neural noise that would make it hard for you to think clearly and remember new things. Your brain needs a way to keep the signal-to-noise ratio of neural communication stable. Sleep is the answer to this problem because it is both useful and very healing. Your brain weakens the strength of synaptic connections while you sleep, especially during the deep stages we'll talk about in a minute. This might sound counterproductive. Why would your brain weaken the connections that hold your memories and knowledge? But this process is actually very complicated. It doesn't make all connections weaker in the same way. Instead, it acts like a skilled editor, keeping the most important and meaningful connections while letting the weaker, less important ones fade away. This synaptic scaling has two great purposes. First, it clears out the neural equivalent of yesterday's newspaper, which is information that was important for a short time but doesn't need to be kept forever. This makes room for new learning. Second, it makes the signal-to-noise ratio of really important memories stronger, which makes them stand out more clearly from the background of everyday life. Your brain seems to lovingly curate the museum of your mind every night, deciding which exhibits should be on display and which should be put away or let go. Several molecular mechanisms that work during sleep are responsible for synaptic scaling. One of the most important ones is the control of proteins that affect the strength of synaptic connections. When you're awake, these proteins build up at synapses in response to brain activity. But while you sleep, other proteins become active that can change or remove these synaptic proteins. This effectively downscales the strength of connections throughout the brain. This downscaling isn't random, it's based on what happened the day before. Synapses that were used a lot and were part of important memories are more likely to be kept or even made stronger. Synapses that were only weakly or rarely activated are more likely to be reduced in size. In this way, sleep acts like a natural selection process for memories, keeping the ones that matter and getting rid of the ones that don't. But getting ready for sleep goes far beyond your brain. As your peripheral nervous system, the network of nerves that connects your brain and spinal cord to the rest of your body, adjusts to the rhythms of night, a similar change is happening throughout your body. As bedtime approaches, your autonomic nervous system, which controls the involuntary functions that keep you alive, also starts to change. The sympathetic nervous system gets your body ready for action during the day, while the parasympathetic nervous system promotes rest and recovery. These two parts of the system usually work together in a careful way. As sleep nears, your nervous system smoothly transitions from sympathetic to parasympathetic dominance. The sympathetic nervous system, which kept you awake and ready to face challenges all day, starts to lose its power. This system works by releasing neurotransmitters like norepinephrine and epinephrine, adrenaline, which speed up the heart rate, breathing rate, blood pressure, and muscle tension. These changes are great for the busy demands of daytime life, but they don't work with the quiet restoration that sleep needs. You can feel the changes in your body as sympathetic activity goes down. Your heart rate slows down from its daytime speed. When you are awake and active, it might be 70 to 80 beats per minute, but when you are in deep sleep, it is only 60 beats per minute or less. Your breathing becomes deeper and more regular as you go from the erratic patterns of waking breathing to the slow, steady rhythm of sleep breathing. As your blood vessels relax, your blood pressure goes down a little. This drop in blood pressure is good for both the heart and the brain's nightly maintenance activities. Lower blood pressure lets cerebrospinal fluid move more freely through neural tissue, which helps the body get rid of waste while you sleep. Your pupils, which opened up during the day to let in more light and keep you awake, start to close. The parasympathetic nervous system controls this pupillary constriction, which is part of the body's overall shift toward rest and saving energy. Your digestive system even starts to change how it works to get ready for the different metabolic needs of sleep. It's like your body is slowly and gently letting go of the stress it needed to get you through the day's tasks. The muscles that kept you standing up start to relax. The muscles in your face relax, which makes your expression calm and neutral. The small muscles around your eyes start to relax too. Your parasympathetic nervous system, which is also known as the rest and digest system, starts to take over at the same time. This is the part of your nervous system that helps you heal, grow, and get better. The parasympathetic system works with different pathways and neurotransmitters than the sympathetic system. It uses chemicals like acetylcholine to help you relax and recover. When the parasympathetic system is active, your digestive system works harder to break down the nutrients from the day while you sleep. To break down any food that is still in your stomach, it makes more acid. Your intestines contract more to move nutrients through your body. Your liver makes more proteins and other molecules that cells need to heal themselves. This is why eating a big meal right before bed can sometimes make it hard to sleep. Your digestive system is working hard and needs energy and attention. When you sleep, your immune system also becomes more active. You might think of sleep as a time when you don't do much, but your immune system actually works harder while you sleep. During sleep, the number of some types of white blood cells goes up. Cytokines, which are signaling molecules that help the immune system work together, are made in a certain way that peaks at night. This immune system activation while you sleep has a number of important purposes. It helps your body fight off infections that you might have come into contact with during the day. It helps fix tissues that were hurt by normal wear and tear, and it helps to strengthen your immune system's memory, which makes it easier for you to deal with threats in the future. Your parasympathetic nervous system also tells your pituitary gland to release growth hormone. This hormone is very important for repairing tissues, growing muscles, and doing all the other cellular maintenance tasks that keep your body healthy. It reaches its highest level during deep sleep. Growth hormone literally makes kids and teens taller overnight by speeding up the growth of bones and other tissues. In adults, growth hormone is still very important for healing and restoring health. It works all the time, even when people are asleep. During sleep, growth hormone is released in a very specific way. The most sleep occurs in the first few hours, especially during the deep, slow-wave sleep stages. This timing makes sense from a biological point of view, because growth hormone works best when the body is at rest and not busy with other metabolic needs. The hormone helps the body make proteins, break down fats, and fix tissues all over the body. Growth hormone also has big effects on your nervous system. It helps neurons grow and stay healthy, makes new synaptic connections, and helps repair neural tissue that may have been hurt during the day. You wake up every morning with a nervous system that has been refreshed and renewed by the growth hormone that is released while you sleep. Your core body temperature starts to drop as your body gets used to this parasympathetic state. This may seem like a simple physical reaction to not moving, but it's actually a complex biological signal that helps set the time for sleep. Every day, your body temperature rises during the day to help your metabolism work and falls at night to help you sleep. The drop in temperature that happens before sleep is both a cause and an effect of the sleep process. Your brain's master clock tells you it's time to go to bed, which starts processes that help you lose heat. Blood vessels close to your skin widen to let warmth escape into the air. You might naturally want to sleep in a cooler place or change your clothes to help you lose heat. Your hypothalamus, which is a part of your brain that controls your body's temperature, is in charge of this cooling process. There are special neurons in the hypothalamus that can sense changes in body temperature and tell the body how to react. As the sun goes down, these thermosensitive neurons start to cool your body down so that you can sleep. The link between sleep and temperature is very clear. Your core body temperature usually drops by 1 to 2 degrees Fahrenheit while you sleep. The lowest point is usually between 4 and 6 a.m. This is the lowest temperature at which you are most likely to feel sleepy if you are awake, and the hardest time to stay awake. This temperature pattern can help explain a lot of things that happen when you sleep. That's why a lot of people naturally put their feet out from under the covers when they sleep. The hands and feet are important places for heat to escape, and cooling these parts of the body helps lower the overall core temperature. This is why a cool room often feels better for sleeping than a warm one. Your body is naturally cooling down, and this is why a warm bath before bed can actually help you sleep, even though it seems like it would make you sleep less. The warm bath makes your blood vessels open up, and when you get out, The quick cooling helps your body get ready for sleep. One of the many things your nervous system uses to start the complex process of falling asleep is temperature. Your body's temperature receptors send information to your brain about the temperature of the environment. This information is combined with other signals about the time of day, the amount of light, and the pressure to sleep inside your body to figure out the best time to sleep. It's a great example of how your body's different systems talk to each other using the same language of chemistry and physics. Your nervous system doesn't work alone. It gets information from your cardiovascular system, endocrine system, immune system, and even the temperature of your skin all the time. It then uses this information to create a coordinated response that helps you fall asleep faster. Now that your nervous system is getting used to its nighttime routine, you are starting to sleep properly for the first time. There are different stages of sleep, and each one has its own pattern of brain activity and role in restoring your body at night. Electroencephalography, EEG, is a method that uses electrodes placed on your scalp to measure the electrical activity of your brain. This is how these stages were found. The first stage is called N1 sleep, which stands for non-REM, or non-rapid eye movement sleep. This name sets it apart from REM sleep, which we'll talk about later on our journey. N1 sleep is the gentle shift from being awake to being asleep. It is a liminal state that usually lasts only a few minutes, but is a very important link between the conscious and unconscious worlds. During N1 sleep, your brain waves slow down even more into the theta range we talked about before. This makes long rolling waves of electrical activity that move across your cortex like gentle swells across a calm ocean. These theta waves, which go around 4 to 8 times per second, show a big change in how your neurons talk to each other. When you're awake and paying attention, your brain waves are usually in the beta range, 13 to 30 Hz. When you're relaxed, they're usually in the alpha range, 8 to 13 Hz. These higher frequencies help with the quick processing of information and making decisions that conscious awareness needs. But when you go into N1 sleep, the slower theta rhythms take over. This shows that your brain is no longer trying to stay active in the world around you. You go from being awake to being asleep when your brain waves change from alpha to theta. People often say that they lose awareness of their surroundings at this point, even though they may still be somewhat responsive to things happening around them. During N1 sleep, you are still somewhat aware of your surroundings, but your awareness has become dreamy and detached. This is because your brain is going through different neural rhythms as it transitions. You might have hypnagogic hallucinations at this point. These are short, vivid images or feelings that seem to come out of nowhere. These aren't real dreams yet. They're just the first signs that the unconscious mind is starting to speak. You might see flashes of colour, hear bits of conversation, or feel like you're falling. This is the classic hypnic jerk that wakes people up during this time. Hypnagogic hallucinations happen when your brain is learning how to work in a new way. Your sensory systems work together to make sense of the world around you when you are awake. Your visual system takes in real images from your surroundings. Your auditory system takes in real sounds, and your brain combines all of this information into your conscious mind. But this sensory integration isn't as reliable during the N1 transition. The thalamus is starting to block sensory information, which slows down the flow of signals from outside to your cortex. Your brain is also starting to make its own patterns of activity that will eventually turn into dreams. The hypnagogic phenomena of N1 sleep show how these two processes are similar. Bits of brain activity mix with less sensory information that is still there. These things happen because your thalamus is still partly open to the outside world. This lets bits of sensory information mix with the first stages of brain activity that are like dreams. Your mind is learning to speak a new language, the language of dreams, and these hypnagogic experiences are its first tentative words. The hypnic jerk, which is the sudden feeling of falling that can wake you up just as you're about to fall asleep, is your brain's way of protecting you during this risky time. When your muscles start to relax in preparation for sleep, your brain sometimes misreads this as a sign of danger and causes a reflexive muscle contraction that briefly wakes you up. It's an evolutionary remnant. a way to protect ourselves that may have helped our ancestors avoid falling out of trees or other high places where they slept. Your muscle tone starts to drop during N1 sleep, but you're not completely paralyzed yet. That will happen later. Your breathing gets more regular, but it's not yet as slow and deep as it will be. Your heart rate is still slowing down, but it hasn't reached the lowest point it can go while you sleep. N1 is a real transition state, a soft bridge between being awake and being deeply asleep. In healthy adults, this first stage of sleep usually lasts only 5 to 10 minutes, but don't let its shortness fool you into thinking it's not important. N1 sleep is an important neurological milestone because it's when your brain stops being awake and starts the sleep process. People who have trouble making this change may have trouble sleeping and lie awake for hours, unable to cross this line. When you go from N1 sleep to N2 sleep, your nervous system crosses a clearer line into unconsciousness. N2 sleep is the most important part of your sleep. In healthy adults, it usually makes up about 45 to 55% of the total time spent sleeping. This is when your brain really starts to show the unique electrical patterns of sleep, which are different from anything else that happens when you're awake. During N2 sleep, your EEG starts to show two things that sleep researchers call sleep spindles and K complexes. These unique wave patterns are so reliable that they are used to define this stage of sleep. Researchers who study sleep know that the brain has definitely gone to sleep when they see it on an EEG recording. Sleep spindles are short bursts of rhythmic brainwave activity that happen every few seconds during N2 sleep and last for about 0.5 to 1 second. Their name comes from how they look on an EEG readout, where they look like the spindle shape of a football spinning through the air, an amplitude that rises quickly and then falls slowly. These spindles usually happen 12 to 14 times per second, which is in the lower part of the beta range. However, their burst-like pattern sets them apart from waking beta activity. Your thalamus, which has been slowly closing the gates to outside awareness, makes sleep spindles. But instead of just blocking information, your thalamus starts to make these rhythmic bursts of activity during N2 sleep that serve many purposes. The spindles help you stay asleep by stopping sensory information from getting to the cortex, but they do this in a way that lets important signals through. Sleep spindles are like a high-tech alarm system for your brain while you sleep. They make it so that people don't respond as much to things outside of themselves for a while, but they also make it so that important information can still get to the brain if it needs to. Even though both sounds are at about the same volume, a parent who is sleeping through normal household noises might wake up right away when they hear their baby crying. The brain's sleep spindle system helps us tell the difference between these important things. Studies have demonstrated that individuals who produce a greater quantity of sleep spindles generally experience more restorative sleep and report enhanced sleep quality. The spindles seem to show that the brain can keep you asleep even when things around you are hard. People who have trouble sleeping often have less sleep spindle activity, which suggests that their brains may have trouble keeping the protective barriers that let them sleep without interruptions. The thalamus has a complicated circuit that makes sleep spindles. Reticular thalamic neurons, which are a type of neuron, act as pacemakers by sending out rhythmic bursts of inhibitory activity that make the spindle pattern. These neurons get information from both the cortex and other thalamic areas. This lets them change the frequency and intensity of the spindle based on how the brain is doing overall. It's interesting that the frequency of sleep spindles differs from person to person. This could be because of genetic differences in how the brain is built and works. Some people naturally make spindles at the lower end of the frequency range, about 11 to 12 hertz, while others make spindles that are faster, 13 to 15 hertz. These individual differences seem to stay the same over time, almost like a neural fingerprint that shows how each person sleeps differently. K complexes are even more interesting than sleep spindles. These are big, slow waves that show up on the EEG all of a sudden, like gentle giants walking across the landscape of your sleeping mind. A K complex is a pattern that lasts for several seconds and looks like a sharp negative wave followed by a slower positive wave. They happen on their own during N2 sleep, but they can also be caused by sounds or other things from the outside world. It's amazing that K complexes can be triggered by things outside of the body. Your nervous system keeps an eye on things even when you're asleep and mostly cut off from the outside world. It can spot and assess possible threats or important information. When your brain is asleep and hears a sound that might need your attention, it makes a K complex to quickly check if the sound is important enough to wake you up. You don't even know that this process is happening because it happens so quickly. Your brain hears the sound, decides it's not important enough to wake you up, and lets you keep sleeping peacefully. Your brain only starts to wake you up when it hears something that is really important, like a baby's cry, a smoke alarm, or someone calling your name. Internal events in the brain itself can also cause K complexes. They can happen when someone wakes up briefly or is aroused but doesn't reach the level of consciousness. The K complex seems to be a way to actively keep the arousal down and keep the sleep going in these situations. Your brain seems to be saying, "No, we're sleeping now," and is working hard to keep you from waking up. Several parts of the brain need to work together to make K complexes. The first sharp wave seems to come from the frontal cortex, while the slower wave seems to come from deeper brain areas like the thalamus. This distributed generation implies that K complexes signify a comprehensive cerebral response to potential sleep disturbances, reflecting a synchronized endeavor by the nervous system to preserve a tranquil state of rest. Sleep spindles and K complexes both help keep your sleep from being disturbed, while still letting your brain respond to things that are really important. They are elegant answers to one of the most important problems with sleep: how to be unconscious and restorative while still being safe and able to respond to real emergencies. Your brain does this while you sleep by using these complex patterns of neural activity that can tell the difference between what's important and what's not. Your body keeps relaxing slowly during N2 sleep. Your heart rate and breathing slow down and become more regular than they were in N1. Your core body temperature keeps going down until it reaches its lowest point at night. Most importantly, your muscle tone drops a lot compared to when you wake up, but not as much as it will during the REM sleep we'll talk about later. Your brainstem controls this drop in muscle tone during N2 sleep through a complicated network of inhibitory signals. Neurons in the pons and medulla send signals down your spinal cord that make the motor neurons that control your voluntary muscles less excitable. This makes your muscles relax more deeply than you can do on your own while you're awake. N2 sleep relaxes your muscles, which is important for a number of reasons. It lowers the amount of energy your body uses, which lets it focus its resources on repairing and restoring itself. It stops you from doing any movements that might happen in your dreams, or when you're mentally active while you sleep. And it might help improve the way blood flows through your body, which helps your heart rest while you sleep. Scientists call this muscle atonia, and it is controlled by your brainstem through the release of certain neurotransmitters. Glycine and GABA are both inhibitory neurotransmitters that are released at synapses in your spinal cord. This disconnects your motor cortex from your muscles. It's a short-term paralysis that can be fully reversed. It keeps your body still and safe while your brain does its nightly repair work. One of the biggest changes in the brain during the whole sleep cycle happens when you go from N2 to N3 sleep, which is also called slow wave sleep or deep sleep. The brain waves during N3 sleep are the slowest of the whole sleep cycle. They are big rolling delta waves that move across your cortex at a slow pace of less than 4 cycles per second. These are the most in-sync brain waves your nervous system can make. This level of neural coordination is impossible when you're awake. When you think about what they mean, the delta waves of deep sleep are really amazing. Your billions of neurons tend to fire independently when you're awake, which creates the complex, chaotic patterns of electrical activity that support the wide range of conscious thought. You can pay attention to one thing while other things happen in the background, switch quickly between different types of thinking, and keep track of more than one stream of information at the same time. But during N3 sleep, something amazing happens. Millions and millions of neurons start to fire together in slow, coordinated bursts. It's like a huge, disorganized crowd suddenly starts marching in perfect time. This firing in sync makes the delta waves that are big and slow, which are what deep sleep is all about. EEG electrodes can even pick up these waves through the skull and scalp. Your brain can do things that would be impossible when you are awake and your neurons are firing randomly. The slow, coordinated waves of N3 sleep seem to work like a gentle tide, moving through your brain and taking away the metabolic waste that built up during the day. Recent studies have shown that during deep sleep, the gaps between your brain cells can grow by as much as 60%. This lets cerebrospinal fluid move more freely through neural tissue and get rid of toxins. This discovery has changed everything we thought we knew about why we sleep. Your brain doesn't have a regular lymphatic system like other organs in your body do to get rid of waste. Instead, it uses this glymphatic system, which is a network of fluid-filled channels that work hard while you sleep. The synchronized neural activity during deep sleep seems to cause the pulsating flow of cerebrospinal fluid that powers this cleaning system. The waste products removed during this nightly cleansing include some that are directly related to neurodegenerative diseases. People with Alzheimer's disease have a lot of amyloid beta, a protein that builds up in their brains. Deep sleep helps get rid of this protein more quickly. During these times of increased waste clearance, the tau protein, which is linked to different types of dementia, is also processed. Some scientists now think that this nightly cleansing process is one of the main reasons we sleep. Your brain makes metabolic waste products as a normal part of neural activity, just like your muscles make lactic acid when you work out. But your brain needs this special state of synchronized slow wave activity to open the pathways for effective waste removal. Muscles can be rested and cleaned separately, so the amount of deep sleep you get may have a big effect on the health of your brain in the long run. People who don't get enough deep sleep on a regular basis may not be getting rid of these waste products from their brains well enough, which could make them more likely to get neurodegenerative diseases later in life. It reminds us how important it is to get good sleep as we get older to keep our brains healthy. Your brain also works on memory consolidation while you are in deep sleep, as we talked about before. The slow waves of N3 sleep seem to help move information from temporary storage areas in your hippocampus to more permanent storage areas in your cortex. This process involves the synchronized replay of patterns of neural activity that were formed during learning. When you learn something new during the day, groups of neurons in your hippocampus fire together in certain ways to store the new information. During deep sleep, these same groups of neurons spontaneously reactivate, firing in the same patterns but much faster than when the person first learned the information. This faster replay seems to help move memory traces from the hippocampus to the cortex, where they can be combined with what you already know and stored for longer. The process works very well. During sleep, a pattern of neural activity that might have taken several seconds to form while learning can be played back in just a few milliseconds. This time compression lets your brain go over and solidify a lot of information during the short hours of deep sleep. It's like watching a fast-paced movie of your day's events, with your brain picking and choosing which scenes should be kept in your permanent memory. This process of consolidating memories is why getting a good night's sleep after learning something new can make it much easier to remember and understand the next day. Students who stay up all night studying for tests are actually stopping their brains from doing the work that would help them do better. The information might be in their hippocampus for a short time, but without the consolidation that happens during deep sleep, a lot of it will be lost or not fit in well with what they already know. It looks like the slow waves of deep sleep also help with synaptic homeostasis, which is the process of keeping the connections between neurons strong. When you're awake, synapses all over your brain get stronger as you learn and have new experiences. But you need to find a balance in this process so that your neural networks don't get too much information. When you're in deep sleep, the synchronized slow waves seem to send a global reset signal that lowers the strength of synapses all over the cortex. This downscaling doesn't get rid of memories. Instead, it makes the overall strength of synaptic connections normal, while keeping the relative differences that encode specific memories. It's like turning down the volume on an entire sound system to keep the instruments at the same level of loudness without making them sound bad. The release of growth hormone that happens most during deep sleep also helps your nervous system heal physically. Even though neurons are very advanced, they are still living cells that need to be cared for and fixed. As they break down over time, the proteins that make up their structure need to be replaced. It is important to keep the membranes that control the flow of electrical signals in good shape. Based on what happens during the day, the synapses that connect one neuron to another need to be made stronger, weaker, or replaced. Growth hormone helps all of these things happen by making proteins in the nervous system. When you sleep deeply, your neurons make more of the proteins they need to keep their structure, fix cells, and keep synapses working. This is why deep sleep is so important for healing brain injuries or when you're learning a lot. Your nervous system literally rebuilds itself while you sleep. The amount of deep sleep you get follows patterns that are easy to predict over your lifetime. Kids and teens spend a lot more time in deep sleep than adults do. This is because their brains are still growing and they are learning and growing a lot during these times. Young children may spend 20 to 25% of their total sleep time in deep sleep, while healthy adults usually spend 15 to 20%. As we get older, we gradually get less deep sleep. Older adults might only spend 5 to 10% of their sleep time in the deepest stages, and some might not even get any deep sleep at all. This decrease in deep sleep that comes with age may be linked to some of the cognitive changes that come with aging, such as less memory consolidation and a higher risk of neurodegenerative diseases. As we get older, our brains change in ways that make it harder for us to get deep sleep. The brain areas that make slow waves, especially the frontal cortex, change with age in ways that can make it harder for them to make the synchronized activity that is needed for deep sleep. Researchers are looking into ways to help people keep their deep sleep as they get older, because they understand these changes. As N3 sleep gets deeper, usually in the first third of the night, your nervous system gets very close to perfect rest. Your brain waves are moving the slowest and most in sync. Your body temperature has dropped to its lowest point for the night. Your heart rate and breathing are at their most relaxed right now. The protective mechanisms in your brainstem keep your muscles in a gentle suspension, making you feel more relaxed than ever. Deep sleep is when your blood pressure drops to its lowest point of the day. This gives your heart and blood vessels a much-needed break and time to heal. The lower pressure lets your heart work less hard while still making sure that all your organs get enough blood flow. People who don't get enough deep sleep are more likely to have high blood pressure and other heart problems because this cardiovascular rest is so important. During deep sleep, your immune system is at its most active, and different types of immune cells move around your body more quickly. During sleep, your body makes more antibodies that fight infections, and your immune system's memory, its ability to remember and respond to future threats, gets stronger. This is why you often feel better after sleeping when you're sick, and why not getting enough sleep makes you more likely to get sick. Your endocrine system also goes through big changes while you sleep deeply. Your body releases other hormones besides growth hormone that help with repair and restoration. During sleep, prolactin, a hormone that helps the immune system and tissue repair, reaches its highest level. Melatonin keeps moving around your body, helping cells fight off free radicals. Your body's ability to process glucose and keep blood sugar levels stable changes while you sleep. An outside observer might think that this is a state of complete inactivity, but that couldn't be more wrong. When you sleep deeply, your nervous system is like a master craftsman working in a well-organized workshop. Every tool is in its place, every process is optimized, and every action is planned and effective. The calmness on the outside hides an amazing symphony of cellular activity, all aimed at healing, strengthening, and getting ready for the next day's events. The neurons in your cortex fire in slow, coordinated patterns. This makes the cerebrospinal fluid flow, which cleans up waste from your brain. Your hippocampus is playing back memories from the day and moving them to places where they will stay forever. Growth hormone is making new proteins in your nervous system that are needed for cell maintenance and repair. Your autonomic nervous system still carefully controls your heart rate, breathing, and other vital functions, but at a lower level that is right for deep sleep. Your temperature control system keeps your core temperature low while making sure that your vital organs stay warm enough. While you sleep, your immune system is on high alert, looking for and destroying any possible threats. Your nervous system starts to wake you up slowly from a deep sleep, but not in a straight line. Instead, it goes in a circle that repeats all night, going from N3 to N2, and then to N1 for a short time before going into the most interesting and mysterious stage of sleep, REM, or rapid eye movement sleep. One of the most dramatic changes in all of neuroscience is the change from deep sleep to REM sleep. Deep sleep is like a quiet, organized workshop where things get done in perfect harmony. REM sleep is like a lively theatre where your mind's most complex plays happen in vivid, impossible detail. Your brain is almost as active metabolically during REM sleep as it is when you're awake. But this activity is turned inward, which is what makes dreams so rich and complex. When you go into REM sleep, your brain's neurotransmitter systems completely change. The chemicals that were most active during the first stages of sleep, like GABA, adenosine, and the slow wave generating mechanisms, start to fade into the background. Your brain starts to release acetylcholine instead. This is the same neurotransmitter that keeps you awake and focused during the day. Acetylcholine, on the other hand, during REM sleep makes you focus on the theatre of your own mind instead of the outside world. The brainstem areas that make REM sleep happen, especially the pons, start sending signals to your nervous system that make this stage different. These neurons in the brainstem fire in strong bursts that travel up to your thalamus and cortex, making the high-frequency brain waves that are common during REM sleep. At the same time, they send signals down to your spinal cord that cause the most severe muscle paralysis of the entire sleep cycle. Your eyes start to move quickly from side to side under your eyelids, following the pictures in your dreams. This stage of sleep is called REM sleep because of the rapid eye movements that happen during it. The eye movements are not random. They seem to match the visual content of dreams, as if you are actually watching the scenes play out in your sleep. During REM sleep, your breathing changes a lot. Sometimes it's fast and shallow, and other times it's deep and slow. This depends on what you're dreaming about. When you dream about running, your breathing might speed up as if you were really doing it. If you dream about having a calm conversation, your breathing might be slower and more regular. Your heart rate also changes more, depending on how you feel about the things in your dreams. During REM sleep, your brain waves change from the slow, synchronized patterns of deep sleep to faster, more chaotic rhythms that are very similar to those of waking consciousness. Gamma waves and beta waves come back. Gamma waves are some of the fastest brain waves your nervous system makes. This high-frequency activity shows how much work your brain does while you sleep, creating complex sensory experiences, emotions, and stories all on its own. But the most interesting thing is that your muscles relax even more during REM sleep. During the early stages of sleep, you are gently paralyzed, but during REM sleep, you become almost completely still. The only parts of your body that are still moving are your diaphragm, which keeps you breathing, and the tiny muscles that move your eyes. This full relaxation of the muscles is very important for REM sleep because dreams can be very real and active. Neurons in your brainstem release glycine and GABA at synapses all over your spinal cord, which causes the muscle paralysis of REM sleep. These neurotransmitters stop your motor cortex from connecting to your voluntary muscles, which keeps the things you might do in your dreams, running, fighting, dancing, flying, safely in your sleeping mind. This protective paralysis is so strong that if you could somehow wake up from REM sleep right away, you wouldn't be able to move for a few seconds while your brainstem systems got back to normal motor control. People sometimes experience this condition called sleep paralysis, which makes them aware before the REM atonia has fully worn off. This makes them feel awake but unable to move, which is scary but not dangerous. The dreams that happen during REM sleep are very different from anything else your nervous system makes. They mix memories, feelings, sensations, and imaginary things in ways that would be impossible when you are awake. You might fly through childhood scenes that turn into your current workplace, talk to people who died years ago, or solve hard problems with solutions that make perfect sense in the dream but seem strange when you wake up. These dreams are a result of the unique neural activity that happens during REM sleep. Thalamic gating cuts off most of your sensory systems from the outside world. This makes your brain start to make its own reality using the same neural networks that process real perceptions when you are awake. The visual cortex, which usually processes signals from your eyes, instead responds to signals from your brainstem, which makes dreams so vivid. During REM sleep, your auditory cortex, which usually processes sounds from your ears, reacts to activity in your brain, creating the conversations, music, and sound effects you hear in dreams. The somatosensory cortex makes you feel things in your dreams, like the wind when you're flying, the water when you're swimming, and the touch of things and people in your dream world. During REM sleep, your brain's emotional centers, especially the amygdala and other limbic structures, become very active. This is why dreams can be so emotional, from the joy of dreams that come true to the fear of nightmares. Dreams can make you feel stronger than you do when you're awake, because they don't have the prefrontal cortex to help control your emotional responses. This making of an internal world is good for your nervous system in many ways. Dreams seem to be very important for processing emotions because they let you deal with feelings and events in a safe, simulated setting. REM sleep's strong emotional activation may help you deal with traumatic or stressful events by adding them to your existing emotional framework in a way that makes them less disruptive when you're awake. It also seems that dreams help people come up with new ideas and solve problems. During REM sleep, your brain can connect different pieces of information in ways that might not happen when you're awake and thinking in a more logical, linear way. A lot of artists, scientists, and inventors have said that they have had big ideas in their dreams. This suggests that REM sleep is very important for creative thinking. The strange and impossible things that happen in dreams may be a normal part of this neural process. REM sleep lets your brain explore new combinations of ideas and experiences by temporarily putting aside the rules that govern waking thought. Dreams can help your brain test out new neural connections and pathways that might be useful in real life. For example, you might dream about flying, talking to dead relatives, or moving between places without any trouble. It seems that REM sleep also helps with procedural memory consolidation, which is the process of making skills and habits stronger instead of specific factual memories. Research indicates that individuals acquiring a new motor skill experience heightened REM sleep the subsequent night, with the quantity of REM sleep correlating to skill enhancement. This indicates that REM sleep aids in the consolidation of both the movements and the neural programs governing skilled behavior. Changes in neurotransmitters that happen during REM sleep have big effects on your whole nervous system. REM sleep lowers levels of norepinephrine and serotonin, which doesn't just affect your brain. These chemicals also control many functions of the peripheral nervous system. During REM sleep, norepinephrine levels drop, which may make it harder for the body to control its temperature. This is because norepinephrine usually helps control blood vessel constriction and heat retention. During REM sleep, your body has a harder time keeping your temperature stable, which makes you more sensitive to the temperature around you. You might wake up more often from REM sleep if your sleeping area is too hot or too cold. People may have more vivid dreams in the early morning hours, when REM sleep is most common and room temperatures are usually at their coolest. This could be because they are sensitive to temperature. REM sleep's high levels of acetylcholine also have special effects on your autonomic nervous system. During REM sleep, your heart rate changes more than it does during other stages of sleep. This is called heart rate variability. It seems that the emotional content of dreams is linked to this increased variability. For example, your heart rate may speed up during exciting or scary dream sequences and slow down during calm dream periods. Your breathing patterns during REM sleep also change more often, and they can even stop for a short time or become irregular. These changes in breathing are usually not harmful for healthy people, but they can be more of a problem for people who have sleep apnea or other sleep-disordered breathing conditions. People with breathing-related sleep disorders may find it especially hard to get through REM sleep because the muscle relaxation can make airway obstruction worse. The cycle between REM and non-REM sleep goes on all night, usually in a set pattern called sleep architecture. You spend more time in the deeper stages of non-REM sleep early in the night, when your sleep pressure is highest and your circadian drive to wake up is lowest. You get most of your physical restoration and memory consolidation during these early deep sleep periods, which are very important after a busy day. As the night goes on and you get some of your sleep debt paid off, the REM periods get longer and happen more often. The longest and most vivid REM periods usually happen in the hours just before you naturally wake up, when your body's circadian system is getting ready for the day ahead. This is why you probably remember dreams from the early morning hours. You spend more time in REM sleep, and you are more likely to wake up right after a REM period. The fact that the balance between non-REM and REM sleep changes shows that these stages have different jobs. Deep sleep takes over early in the night, when your body needs to heal the most. As your body gets closer to being fully restored later in the night, REM sleep takes over. This is when your brain processes emotions and integrates memories to get you ready for the mental challenges of a new day. Your circadian clock and your homeostatic sleep drive work together in a complicated way to create the whole pattern. Your circadian system sets the basic times for when you should sleep and wake up, and your homeostatic system keeps track of how long you've been awake and changes the intensity and makeup of your sleep as needed. This two-step process helps make sure you get the right amount of sleep at the right times. Your homeostatic drive will be higher if you go to bed later than usual, which will help you get more deep sleep early in the night. When you're under emotional stress, your brain may need more time or more REM periods to process what you're going through. As dawn approaches and your sleep cycles come to an end, your nervous system starts to slowly bring you back to waking consciousness. This process of waking up is just as carefully planned as the process of going to sleep. It involves the coordinated activation of many brain systems that bring waking function back to normal. Your circadian clock, which has been keeping track of time all night, starts to let you know that it's time to wake up. Even when there are no outside light cues, your suprachiasmatic nucleus can keep track of time pretty well, getting your body ready to wake up at about the right time every day. As morning approaches, your core body temperature, which dropped to its lowest point during deep sleep, begins to rise a little. One of the first signs that your body is getting ready for the metabolic demands of waking up is that your temperature goes up. The warming trend starts even before you wake up, getting your heart and blood vessels ready for the extra activity that will come with being awake. As your pineal gland gets signals from inside your body about the coming dawn, your brain makes less melatonin. Even without light from outside, your circadian system can tell when the next day is coming and start to make less melatonin. When you wake up and see light from outside, it confirms and strengthens this internal timing signal. The cortisol awakening response is when cortisol levels start to rise. This increase in cortisol helps your body use its energy stores and get back to the alert, focused state of waking consciousness. The release of this cortisol is perfectly timed with your body's circadian rhythms. It usually starts 2 to 3 hours before you wake up and reaches its peak shortly after you wake up. But this process of waking up is slow and careful so that your different neural systems can work together to get going. Your thalamus starts to let sensory information back in, slowly making it more responsive to sights, sounds, and other things in the environment. The process slowly turns off the sensory gating that kept you from waking up, so you don't have to deal with the sudden change that would happen if all sensory input came back at once. As your brainstem sends fewer signals that keep your voluntary muscles relaxed while you sleep, your muscle atonia starts to go away. Your protective paralysis is slowly going away as the glycine and GABA that caused it are cleared from spinal synapses. This lets normal motor control come back. It usually takes a few minutes for this to happen, which is why you might feel a little groggy or unsteady when you first wake up. Your brain waves change from the patterns of sleep to the rhythms of waking up. Alpha waves may take over for a short time as you wake up and become fully alert. This is what many people feel when they wake up. As your brain deals with the demands of being aware of your surroundings and thinking about things, beta waves slowly take over. As your waking systems turn back on, the balance of neurotransmitters in your brain changes a lot. As neurons in your brainstem start to work normally again, norepinephrine and serotonin levels, which were low during REM sleep, start to rise. Dopamine systems that help with motivation and processing rewards start working again. Acetylcholine is still important, but now it helps with learning and attention while you're awake instead of making dreams. Your autonomic nervous system switches from being parasympathetic to sympathetic, getting your body ready for the day's activities. Your heart rate goes up from the lowest level it can be while you sleep to the normal level when you wake up. As your body gets used to supporting an active metabolism, your breathing gets deeper and more variable. Your blood pressure goes up as your heart and blood vessels get ready to support standing up and moving around. One of the most amazing things that the brain can do is switch from sleep to wakefulness. Your nervous system goes from being focused on the inside, which is best for healing and processing, to being focused on the outside, which is ready to deal with the complexities of the conscious world. It's like seeing a theatre empty after a show and then turning back into a busy city street. The same neural architecture is there, but it serves a different purpose. Your prefrontal cortex, which was mostly off while you were sleeping, turns back on and starts to give you the executive control that is a sign of mature human consciousness. Working memory comes back online, which lets you keep and work with information in your conscious mind. Attention systems turn back on, letting you focus on important information while ignoring other things that might get in the way. As you wake up, you start to feel the effects of the memory consolidation and synaptic scaling that happened while you were sleeping. Information that was only weakly encoded the day before may now be more firmly stored in memory. Yesterday's problems that seemed impossible to solve might have answers that are clear now. The skills you practiced might come to you more easily and naturally. Your nervous system has been working hard all night to keep you healthy, process what you've been through, and get you ready for the new day's challenges and opportunities. Deep sleep has improved glymphatic flow, which has helped clear metabolic waste from your brain. It has made important memories stronger while letting less important ones fade away, which is the best way to store information for a long time. Your nervous system has processed the emotional events of the day before through the intense limbic activation of REM sleep. This has added them to your ongoing psychological story in ways that help you stay emotionally strong and healthy. The deep sleep hormone release and protein synthesis have kept and repaired the cellular infrastructure of your brain and body. Your immune system has done its nightly patrol, finding and getting rid of possible threats while also strengthening its memory of past encounters. Your endocrine system has set hormone levels back to normal and gotten your body's chemical messengers ready for another day of working together. Your heart and blood vessels have had important hours of less work while still keeping the blood flowing that is needed for healing and repair. This is the gentle miracle of sleep, which your nervous system controls with more accuracy and care than any human-made technology. Every neuron, synapse, and chemical messenger works together perfectly to give you the gift of rest and renewal. The process is so complicated that millions of individual cells work together over many timescales to give you the smooth experience of sleep and waking up that you have every night. And what makes this even more amazing is that you don't have to do anything to make it happen. It happens all on its own. You don't have to remember to slow your heart rate while you sleep, let go of growth hormone while you sleep, or make REM dreams. You don't have to think about when to go to sleep, or remember to wake up your motor systems when you wake up. Your nervous system takes care of all of these complicated details just as well as it takes care of your breathing or your heart beating. All you have to do is make the right conditions for sleep. A comfortable place to sleep, a calm mind, and a body that is ready to sleep. Your nervous system will take care of the rest, with an efficiency and sophistication that will amaze you the more you learn about it. The fact that sleep happens on its own is one of the best things your nervous system does for you. In a world that often requires constant attention and conscious control, sleep provides a refuge where one can relinquish control and have faith in the innate wisdom of one's biology. You don't need to manage, optimize, or control the process of sleep. You just need to let it happen and give in to the gentle guidance of systems that have been getting better and better over millions of years of evolution. Getting ready for bed every night is one of the oldest and most important things people do on Earth. Almost every animal with a nervous system shows some kind of sleep-like behavior. So sleep isn't just for people. The preservation of sleep throughout evolution, despite its apparent susceptibility, underscores its essential role in nervous system functionality. Your sleep is linked to the sleep of many other living things. They all follow the same patterns of rest and activity that have been shaped by the same planetary rhythms of light and darkness that have ruled life for billions of years. Melatonin from your pineal gland is the same chemical as melatonin from other mammals, birds, and even plants. The slow waves that happen when you are in deep sleep are similar to those that happen in other mammals. This evolutionary view adds to the amazement of the nightly journey your nervous system takes you on. You're not just healing and renewing yourself, you're also taking part in a biological process that links you to all life on Earth and follows rhythms that are as basic as the rotation of the planet. Before you go to sleep tonight, take a moment to think about how amazing your body is at keeping you safe while you sleep. Be thankful for the neurons that will slow down their firing to give you peace, the chemicals that will wash through your brain to help you heal, the protective paralysis that will keep you safe while you dream, and the biological clocks that will make sure you wake up at the right time, feeling refreshed and renewed. Think about how the growth hormone will flow through your blood and help your body repair itself and keep cells healthy. While you sleep, your immune cells will be on high alert and will patrol your tissues. Be thankful for the systems that control your temperature, your breathing, and your heart. They will all keep you comfortable and your blood flowing smoothly. Be amazed by the memory consolidation processes that will organize and combine your experiences, making important memories stronger and letting less important ones fade away. Be amazed by the emotional processing systems that will help you stay mentally stable and strong by working through the things that happen during the day. Recognize that REM sleep can help you think outside the box and come up with new ideas and solutions to problems you're having. Your nervous system doesn't ask you for anything in return except the chance to do what it does best. Take care of you with a level of care and accuracy that knows no bounds. It doesn't need to be managed or controlled on purpose. You don't have to understand or appreciate it, but doing so can help you get to know this amazing system better. It just wants to serve you and give you the rest and restoration you need to thrive. When you start to fall asleep and your mind starts to fade, billions of cells hold you in their gentle embrace. Their only goal is to give you the rest you need to thrive. Have faith in that hug. Let your own beautiful, complicated, and caring nervous system take you to sleep. Think about how amazing what is about to happen is. When you lie still in bed, your brain will start to make slow waves that will wash away the metabolic waste from the day. Your hippocampus will quickly replay the events of the day, moving important memories to long-term storage and letting unimportant ones fade away. While you sleep, your immune system will work harder, sending out cellular guards to protect and fix your body. Your levels of growth hormone will rise, which will help your body's tissues repair and maintain themselves. Your brain will get rid of harmful proteins that could build up and cause problems over time. Your heart will get a break during this time of lower demand, but it will still need to circulate blood to help it heal. In a few hours, you'll be in REM sleep, which is like a theatre where your brain makes up amazing, impossible worlds using memories, feelings, and imagination. You'll fly through places that only exist in your dreams. You'll use the free imaginative logic of dreams to figure things out. While you sleep, you'll work through your feelings in a safe place, adding what happened during the day to your ongoing psychological story. You won't have to do anything to make any of this happen. You don't have to worry about directing the process or whether it's working right. Your nervous system has been perfecting these procedures for your entire lifetime and for countless generations before you. It knows exactly what to do and when to do it. You just have to let it happen. Imagine that your nervous system is the most caring caregiver you can think of. It never sleeps, takes breaks, or stops working for your health. It doesn't ask for thanks or recognition, but both are fine. It just keeps serving you faithfully, day and night. making sure you have everything you need to live, learn, love, and grow. This caregiver knows you better than you do. It keeps track of every breath you've taken, every heartbeat, and every time you've slept or woken up in your life. It has learned to give you the best rest and recovery based on your own patterns and preferences. It can tell when you need more REM sleep and when you need more deep sleep. It knows how to change your sleep schedule based on what you've been through recently and what you need right now. Your nervous system also links you to something bigger than yourself, the rhythms of nature and the cycles of light and dark that have been in charge of life on Earth for billions of years. As you sleep tonight, you're taking part in a process that connects you to every other sleeping animal on Earth, from the tiniest mammals to the biggest whales. They all follow the same patterns of rest and recovery. The melatonin in your blood right now is chemically the same as the melatonin in a sleeping mouse, a resting bird, or even some plants that have daily cycles of activity and rest. The slow waves that are building up in your cortex follow the same basic patterns that other mammals' brains do when they sleep. Right now, billions of nervous systems around the world are settling down to sleep. You're part of a huge biological symphony. It can be very comforting to feel connected to the bigger patterns of life. Sleep is not an isolated occurrence. It is an integral component of the fundamental rhythm of existence. The same forces that change the seasons and pull the tides are gently pushing you to rest. The earth is spinning under you, which helps you sleep at the right times. Not only does your bed hold you up, but the whole planet does too. As you start to fall asleep, pay attention to the small changes that are happening in your body and mind. Your breathing is getting slower and more regular. Your heart rate is starting to slow down for the night. Your muscles are starting to let go of the stress they held on to all day. Your thoughts are getting less clear and more like dreams. These changes aren't happening by chance. They're the result of very complex biological processes that your nervous system is controlling with perfect timing. Your brainstem's neurons are making fewer neurotransmitters that help you wake up. Your thalamus is starting to block out sensory information, which keeps your sleep from being disturbed by things that don't need to be. Your pineal gland is sending melatonin into your blood like a soft chemical lullaby. You can fully trust these steps. They have been tested and improved over millions of years of evolution. They've safely carried your ancestors through the night for many generations. They've been working hard for you since before you were born, and they'll keep doing so until you die. You are in the care of the most advanced, dependable, and caring system possible. Feel thankful for the hard work they do for you. Your nervous system never complains, asks for time off, or threatens to quit if things aren't perfect at work. It changes to fit whatever situation you put it in. Stress, irregular schedules, or tough environments, and does its best to give you the rest and recovery you need. You should appreciate it and trust it. As you fall asleep, remember that you're not losing consciousness. You're just entering a different state of consciousness. Your brain will still be busy all night, but it will be busy with things that are going on inside of you instead of outside of you. It won't take in information from the outside world. Instead, it will take in information from your own world, like your memories, feelings, experiences, and dreams. This inward focus doesn't mean turning away from life. It means getting more involved with it. Your brain will try to make sense of and connect your experiences while you sleep, which it can't do when you're awake. It will find links between things that don't seem to be related. It will deal with problems and feelings that come up. It will help you remember the most important things and let less important things fade away. Your nervous system will also use this time to do important maintenance that keeps you healthy and working at your best. It will get rid of the waste products that cells built up during the day. It will fix damage to neurons and other tissues. It will make your immune system stronger and get it ready for the challenges of tomorrow. It will help your physical and mental health by balancing the levels of neurotransmitters and hormones in your body. When you're completely at rest, your nervous system doesn't have to split its attention between maintenance tasks and the demands of conscious awareness. This is when all of this restorative work happens most efficiently. This is why sleep is so important. It's not just a break from activity, it's also a time when your body's most important biological processes can work at their best. You might notice that your thoughts become more fluid and connected as you fall asleep. Memories from different times in your life may start to mix together. Images that look real might turn into images that look like dreams. This is your brain starting to work in sleep mode when the rules of logic and cause and effect become less strict. Don't fight these changes or try to stay awake. Let your mind go where it wants to. Even if what your brain does while you sleep seems strange or illogical to you when you're awake, you should trust that it knows what it's doing. Sleep's associative thinking is very important because it helps your brain make new connections, deal with emotions, and combine experiences in new and interesting ways. Your nervous system is getting ready to take you on a journey through different levels of consciousness, each of which has its own health and wellness benefits. You'll go from the lighter stages of sleep to the deep sleep stage, where your brain waves will slow down to their most synchronized rhythms, and your body will reach its deepest state of relaxation and restoration. Later in the night, you'll go into the bright theater of REM sleep, where your brain will make up detailed dreams using memory and imagination. You could fly, meet people from your past, or find answers to problems that seemed impossible during the day. All of this will happen on its own, thanks to the complex neural processes that control how dreams are made. During these times of deep sleep and dreaming, you'll go through lighter stages that connect different types of unconscious experiences. Your sleep won't be a single uniform state. Instead, it will be a carefully planned series of different neural activities, each of which will help you recover and feel better overall. Your nervous system will always be on the lookout for your safety during this whole journey. It will keep an eye on your surroundings for sounds or other things that might need your attention. It will keep your heart rate, breathing, and other important functions going. It will make sure you are in the right place and comfortable. You can sleep soundly knowing that the most devoted guardian you'll ever have is watching over you. The way your nervous system protects you while you sleep is very advanced. It can tell the difference between sounds that are just annoying and those that could mean danger. It can tell when the temperature, air quality, or other environmental factors that might affect your comfort or safety change. It can even respond to your dreams, keeping you from doing potentially dangerous things in your sleep by putting you in a state of protective paralysis. Your nervous system's job of protecting you goes beyond just keeping you safe. It also keeps your mind healthy while you sleep. When you dream, your mind processes emotions in a safe, controlled space where you can deal with difficult feelings without having to deal with them in real life. Your brain can think about different situations, try out different reactions, and deal with emotions in ways that make you stronger and smarter. As you fall asleep, keep in mind that you're starting one of the most important things you'll do all day. Sleep isn't time taken away from living. It's an important part of a good life. Sleep gives your body the rest and repair it needs to do everything you do while you're awake. Memory consolidation that happens while you sleep is what makes learning and growing possible. Your mental health and strength are helped by the emotional processing that happens while you sleep. Every hour of good sleep is a gift to your future self. The clearing of waste that happens during deep sleep may help keep you from getting neurodegenerative diseases decades from now. When you sleep, your brain strengthens memories. This helps you learn and remember things that will help you for the rest of your life. REM sleep helps you build the mental tools you need to deal with problems that may come up in the future by processing your emotions. Sleep is a gift you give yourself. It's not just a short-term gift of rest and refreshment, but also a long-term gift of good health, mental clarity, and emotional well-being. Your nervous system is the generous benefactor that makes this gift possible. It works hard all night to make sure you wake up refreshed, restored, and ready for whatever the new day may bring. Let go of everything and let the process take over as your mind fades and sleep takes over. Let go of any tension that is still in your muscles. Let go of any worries or thoughts that are still bothering you from the day. Let your breathing find its natural sleep pattern. Give your nervous system all of your trust and let it take care of you. You are about to go through one of the most beautiful and healing processes in all of biology. Your brain will make slow, synchronized waves that will wash through your neural tissue like gentle waves, cleaning up the mess of consciousness and getting ready for new growth. Hormones that help your body heal and grow will be released. Your immune system will be more alert while you sleep, protecting you when you're most vulnerable. In a few hours, you'll enter the amazing world of dreams, where your sleeping brain will mix memories, feelings, and imagination to make experiences that can't happen in real life. You'll go to places that only exist in your mind and meet people who only exist in your dreams. You might also find answers or insights that have been hiding beneath the surface of your mind. All of this will happen in accordance with ancient rhythms that link you to the most fundamental patterns of life on Earth. Your sleep is a basic part of life, just like the beating of your heart, the rhythm of your breathing, and the changing of the seasons. You're taking part in one of the most important and universal things that happen in life. Have faith in this process. Have faith in your nervous system. Have faith in the wisdom of billions of years of evolution that have made these systems for rest and recovery. You don't have to know everything about how sleep works. You just have to let it happen and trust the systems that know exactly what you need. As the last bits of waking consciousness fade away, know that you are safe, protected, and cared for by the best and most devoted system you could ever think of. Your nervous system will keep an eye on your sleep to make sure you get the rest and restoration you need, while also keeping you safe and comfortable all night. And with that trust, that thankfulness, and that complete letting go of your own nervous system's loving care, let yourself fall asleep in peace. With each breath, feel the soft waves of relaxation wash over you, taking you deeper into sleep. Let your own biology's loving embrace keep you safe through the night. You will wake up at the right time, feeling refreshed and ready for the gift of another day. Good night, dear listener. May the symphony of your nervous system be especially beautiful tonight, and may you wake up tomorrow feeling very thankful for the amazing system that makes all of your experiences, both waking and sleeping, possible. You are in the most loving and capable hands possible, your own. So sleep